Hello, you are listening to Night Cosmos Sleep. Thank you for being here during this slower, quieter part of your day. Let everything outside drift a little farther away and join us as we enter a peaceful story about Mars, the red planet that lies close to Earth, yet carries a past very different from the cold, dry world we see today. Mars is more than a red point of light in the sky. It is a world that has inspired many questions. Why does its barren surface contain features resembling riverbeds, ancient lakes, and regions where water may once have existed? How could a planet that may once have been wetter gradually become a place with such a thin atmosphere? On tonight's journey, we will not rush toward a final answer. We will move slowly, one step at a time, from the traces that remain across the red ground to the thin layer of air surrounding the planet, and then to the quiet influence of the sun over billions of years. This is the story of a world that gradually lost much of its atmosphere. And through that story, Mars gently reminds us that the sky, the air, and water, the things that seem so ordinary on Earth, are far more fragile than we often realize. If we could stand safely on the surface of Mars for just a moment, the first thing to surprise us might not be the red color of the rocks and soil, or even the silence stretching all the way to the horizon. The stranger thing would be the space directly above us. There would still be a sky, still sunlight, still dust suspended in the air, and still the faintest movements of wind. But that sky would be nothing like the one we know on Earth. It would be far thinner, far weaker, and not dense enough to protect the planet below in the way Earth's atmosphere quietly does every day. Mars is not a place completely without air. That distinction matters because many people imagine the red planet as a bare sphere of rock resting in the emptiness of space. In reality, Mars still has an atmosphere. It contains carbon dioxide, small amounts of nitrogen and argon, and traces of several other gases. It has winds strong enough to carry dust across great distances. Thin clouds can appear at certain times. Mars still has weather, seasons, and enormous dust storms capable of spreading across much of the surface. But all of this takes place within an extremely thin layer of air. Compared with Earth, the average atmospheric pressure at the Martian surface is less than 1% as great. That number may sound small and abstract, but it changes nearly everything. On Earth, the air surrounding us creates steady pressure. We cannot see it and rarely think about it, yet it is always present. It presses gently against the surface of water, helping liquid water remain stable. It holds onto some warmth. It softens the temperature difference between day and night. It allows clouds to form, rain to fall, winds to carry moisture across continents, and living things to breathe within a relatively stable environment. Earth's atmosphere is like a vast, familiar envelope around us, so ordinary that we often forget we are living inside it. On Mars, that envelope has become far too thin. Sunlight still reaches the ground, but very little warmth is retained. During the day, the surface in some places near the equator can briefly become warmer. But as the sun sinks lower, that heat escapes very quickly. The thin atmosphere cannot preserve the warmth through the night. As a result, Mars can experience extreme changes in temperature. A landscape warmed by daylight can rapidly become deeply cold once darkness settles across it. The fragility of the atmosphere also makes it extremely difficult for water to remain on the Martian surface. On Earth, if we place a glass of water outdoors, it may slowly evaporate or freeze if the weather becomes cold enough, but under ordinary conditions it can remain liquid. On Mars, that is much more difficult. The pressure is so low that liquid water is unstable. If a small amount of water appeared on the surface, it could quickly evaporate, freeze, or change state within a short time. In simpler terms, present-day Mars does not have a sky heavy enough to hold liquid water for long periods in rivers, lakes, or seas. This is one reason the red planet looks so barren. Vast regions extend beneath reddish-brown dust rich in iron. Rocks lie scattered across the ground. Ancient impact craters preserve marks left by meteorites in the distant past. Enormous volcanoes, deep valleys, and cold plains still remain, but no flowing water moves through them as it does on Earth. There are no forests, no oceans, and no sound of rain. There is only a dry, cold world surrounded by a thin atmosphere, like the surviving remnant of something that may once have been very different. Yet this thin atmosphere is precisely what makes Mars so interesting. It has not disappeared completely, but it is no longer strong enough to make the planet an easy place for life. It is like a door left partly open between two states. Mars is not entirely exposed to space, yet neither is it protected in the way Earth is. It still has a sky, but that sky is no longer thick enough to hold heat, preserve water, or soften the harsh conditions at the surface. Because human beings have not yet been able to walk directly on Mars, we send small robotic explorers in our place. These machines are designed to travel across the ground, take photographs, make measurements, and analyze rocks and dust. They are called rovers. In the images they return, Mars often appears almost completely still. The horizon is low. Dust covers the ground. The sky may appear pale yellow, light orange, or reddish gray, depending on how much dust is suspended in the air. The scene can seem peaceful, but it is the peace of an extremely harsh place. Each grain of dust may remain there for a very long time. Each rock may endure millions of years of cold. Entire landscapes may preserve the same appearance across spans of time that are almost impossible for human beings to imagine. And above it all, the thin atmosphere continues to move. It is nothing like Earth's deep ocean of air, but it is still enough to create winds. Those winds may be gentle or strong enough to lift dust from the ground, dim the sunlight, coat the solar panels of spacecraft, or turn an enormous region into a curtain of red haze. On Mars, the wind carries no scent of damp soil after rain. It does not move the fragrance of plants across open fields. It carries mostly dust, extremely fine, dry, and persistent. And because the air is so thin, even its movements behave differently from the winds we know on Earth. What is especially meaningful is that this thin atmosphere is not merely a feature of the present. It is the result of a very long history. Mars was not born with the cold, dry appearance it has today and then left unchanged. Marks preserved across the surface suggest that the planet once had a more complex past. But before we move deeper into that history, it is important to feel the reality of Mars as it exists now. A planet that still has air, but not enough of it, still has weather, but weather very different from Earth's, still has a sky, but one that has become too thin to preserve the conditions that may once have allowed the surface to remain wetter. Once we understand this, Mars is no longer only a distant red point. It becomes a world holding a great question within its cold dryness. What happened to the atmosphere that may once have been thicker? What caused water to stop remaining on the surface as it once did? And why did a planet so close to us within the solar system follow such a different path from Earth? The thin sky of Mars is where that story begins. It shows us the result before we begin tracing the causes. It allows us to see the present before returning to the past. Beneath that fragile atmosphere, dry channels, cracks in the ground, valleys, and ancient curves remain still, as though the surface is preserving a memory that the sky can no longer protect. And from that quiet place, the story of water on Mars begins to emerge more clearly. At first glance, present-day Mars does not appear to be a violent place. It is not burning or surging with energy. There are no storms of light or scenes of chaos like those many people imagine when thinking about an alien world. Instead, the red planet carries a profound stillness. The ground stretches outward in shades of reddish-brown. The sunlight feels paler than the familiar light on Earth, and the horizon lies low and distant, as though the entire world were opening into a silence without end. Even in the harshest deserts on Earth, life still finds ways to remain. A thin layer of mist may settle on rocks in the morning. A rare rainfall may awaken seeds that have rested beneath the sand for a very long time. Even in places that seem almost completely barren, the atmosphere remains thick enough to retain some warmth, carry a little moisture, and prevent day and night from becoming separated too abruptly. Mars is different. Its dryness does not exist only in the soil. It is built into the planet's inability to preserve heat and water the way Earth does. During an afternoon on Mars, sunlight still reaches the surface, but it feels weaker and more distant than anything familiar to us. The landscape may appear pale yellow, light orange, or reddish gray, depending on how much dust is drifting through the atmosphere. Nothing is softened by the green of plants. There is no water reflecting the sky, and no heavy clouds filled with moisture to announce the approach of rain. The beauty there is quiet and immense, but it is the beauty of a place that has moved far away from the conditions that nourish life. Mars still has an atmosphere, but it is far too thin to perform the work Earth's atmosphere carries out every day. On Earth, the air is like a vast cushion surrounding the planet. It preserves some warmth after sunset, softens the change between day and night, and helps liquid water remain stable at the surface. On Mars, that cushion is much thinner. Winds can still blow and dust can still rise, but warmth does not remain for long. The ground may heat slightly beneath the daylight for a brief period, then cool rapidly once the sun disappears. These temperature changes make Mars an extremely difficult place for stable conditions to endure. A region near the equator may receive enough sunlight for the surface to warm a little, but that warmth is as fragile as a brief breath. When night arrives, heat escapes quickly into space. The rocks become cold again. The dust becomes cold again. Plains that were illuminated during the day sink back into deep freezing temperatures. If Earth is like a house with thick walls and a protective roof, then Mars is like a room that can barely hold any warmth, where light enters but cannot remain for long. This is one reason liquid water can scarcely remain stable on the surface of Mars today. On Earth, water can rest in ponds and lakes, flow through rivers, gather into oceans, or fall as rain because the surrounding environment allows it to stay. Water needs suitable temperatures, but it also needs an atmosphere thick enough to press down on the surface. When that pressure becomes too low, water struggles to remain liquid. On Mars, if a small amount of water appeared, it would quickly freeze, evaporate, or change into another state before it could form a lasting flow. The Martian surface, therefore, has a distinctly hard and dry appearance. Rocks lie scattered across broad stretches of ground. Red dust covers slopes, settles into narrow cracks, and clings to the surfaces of the robotic explorers sent there by humanity. Impact craters remain sharply visible, preserving marks left by objects that fell from space in the distant past. On Earth, rain, rivers, oceans, vegetation, and geological activity continually reshape the landscape and erase many ancient traces. On Mars, where water no longer flows across the surface as it once may have, and the environment changes more slowly, many features can remain for immense periods of time. Some places on Mars feel like memories of an age that has dried away. Plains extend beneath red dust. Depressions and deep craters retain their ancient forms. Boulders rest beneath the weak sunlight as though they have grown accustomed to endless cold. Every crack, ridge, and old layer of soil seems to preserve a fragment of time. They tell no story through sound, yet they still create the feeling that this planet has experienced far more change than its present appearance reveals. Farther away, enormous volcanoes stand silently as markers of a time when Mars was much more active. Among them is Olympus Mons, the tallest and largest volcano on Mars, greater than any mountain on Earth. It rises above the red landscape, not only as an immense landform, but also as a reminder that the red planet once had a hotter and more dynamic interior, when lava and geological activity could still reshape the surface. Today, however, those volcanoes no longer tell their stories through fire. They rest in the cold like enormous monuments to the past, making the Martian landscape feel both majestic and lonely. Within this stillness, dust is one of the few things that continues to move regularly. Martian dust is extremely fine and light, and the wind can lift it even through the thin atmosphere. Sometimes it forms small, swirling columns that travel across the ground. At other times, it spreads into enormous storms that dim the sky and weaken the sunlight. The dust carries no moisture and no scent of wet soil after rain. It simply moves across the land as a dry, cold sign of motion, settling over rocks, plains, and ancient features before eventually falling still again. If we imagine a quiet afternoon on Mars, the absences may feel even more striking than the landscape itself. There is no distant sound of waves, no leaves brush against one another, no rain taps against the ground. Even the wind would not sound the way it does on Earth, because the atmosphere is too thin to carry sound strongly. The silence is not only the silence of distance. It is the silence of a surface without flowing water, without vegetation, and without the softer movements associated with life. The longer we look at Mars in this cold and dry condition, the harder it becomes to ignore the signs of water from its past. A planet unable to preserve liquid water today still contains features resembling ancient riverbeds. A surface this dry still holds regions that look as though material was once carried and deposited by flowing water. A world without rainfall like Earth's preserves signs in its rocks that point toward a wetter age. The contrast does not need to be emphasized with dramatic words. The landscape raises the question on its own. Mars is like an old book whose final page is covered in dust. The present page tells of a cold, dry planet with a thin sky where liquid water can barely remain. But the earlier pages have not vanished completely. They remain within curved landforms, stacked layers of rock, dry basins, and the traces of vanished flows. Because the present is so barren, so quiet, and so lacking in water, the wetter past of Mars becomes even more compelling. A cold and dry planet like Mars does more than suggest what has been lost. Its silence makes its past more worthy of attention. The thin atmosphere of today, the lasting cold, and the absence of liquid water at the surface all show that modern Mars is very different from a world that may once have been wetter. Beneath the red dust, within cold slabs of rock and across broad, dry landscapes, the planet still preserves quiet traces of another period. It may have been a time when the atmosphere was thicker, temperatures were more stable, and water remained long enough to move across the ground, leaving behind features that can still be seen today. Looking at Mars today, it is difficult to imagine that water ever existed there. The ground is hard and dry, the sky is thin, and cold settles over the rocks and dust. Everything suggests a world that no longer has a place for rivers or lakes. Yet within that stillness and cold, ancient traces remain. They do not announce themselves loudly. They appear quietly in the shape of the terrain, in layers of rock resting one above another, in depressions and valleys, and in soft, curving features that wind alone would have difficulty creating. Because human beings cannot yet walk across Mars ourselves, we have sent other eyes in our place. Some spacecraft orbit the planet and observe it from above, recording broad sections of the surface. Small robotic vehicles travel slowly across the ground, moving over rocks and dust, taking photographs, drilling into the surface, and analyzing the material within the soil and stone. Through these quiet observers, Mars has begun to reveal another side of itself. It is not only a cold desert, it is also a world that water once touched deeply. Among the clearest signs are dry river channels. Seen from above, some features stretch across the landscape, bending, branching, and joining again, much like the marks left on Earth when rivers flow across the ground for long periods. If only one or two places like this existed, they might be dismissed as coincidences created by rock and wind. But similar landforms appear in many places across Mars. Some valleys look as though flowing water once cut through the surface. Some networks of channels spread outward like the branches of ancient rivers. Other regions appear to have been worn down, carried away, and reshaped by water, leaving curves much softer than the sharp breaks normally found in dry rock. Water did not leave traces only along the paths it once followed. In some places, the surface also preserves the shape of ancient deltas. A delta is a region that commonly forms where a river enters a lake or sea. As the water slows, it begins depositing mud, sand, and gravel in layers that gradually spread outward like a fan. On Earth, such regions are often fertile and full of life. On Mars, they have been dry for an immense amount of time, yet their shapes remain. One of the most famous examples lies in Jezero Crater, where the Perseverance rover landed. From above, the area resembles a delta turned to stone, with ancient branches and layers of material that water once carried there and then released. The water is gone, but the geometry of its movement remains preserved on the ground. Elsewhere, the rocks and terrain show signs of ancient lakes. An old lake bed does not appear as blue water, of course. Instead, it appears as a basin that was once calm enough for mud and sand to settle over time. As this material accumulated, it formed sediment. Sediment can be understood simply as layers of small particles, ranging from mud to fine sand, carried by water or wind, and then deposited in separate beds. On Mars, some places contain evenly stacked rock layers, like thin pages in a book. Their arrangement suggests that wind did not merely pass across the region. The environment may once have remained stable enough for material to settle gradually through water. Gale Crater is one especially important example. There, the Curiosity rover traveled through regions containing layered rock and sediment grains that were too fine and too evenly arranged to be explained only by random impacts. They resemble traces of mud and sand that once rested beneath water and gradually hardened over time. Looking into those layers, we do not see only the present surface of Mars. We see a past in which water did more than briefly pass through. It remained long enough to build thin layers of material, one upon another. The shapes of the landscape are not the only evidence. The composition of the rocks also speaks. Some minerals are present in ways that offer an almost unmistakable reminder of water. Minerals are naturally occurring solid substances that make up rocks. Certain minerals form most easily when rock remains in contact with water for long periods. Clay minerals, for example, often develop when water slowly changes the structure and chemical composition of the original rock. This makes clay an especially valuable clue. When spacecraft and spectroscopic instruments detect clay-rich regions on Mars, they suggest that those places once had wetter, more stable environments, perhaps far gentler than anything found there today. Alongside clay, some regions contain traces of sulfates, minerals commonly associated with evaporating water or with watery environments that had particular chemical conditions. These tell a somewhat different story. Clay may suggest water that remained for a considerable time, while sulfates can point toward shallow bodies of water that gradually dried up, leaving mineral salts behind as the liquid disappeared. By reading these rocks and minerals, scientists move beyond asking whether water once existed. They begin asking what kind of environment the water occupied, how long it remained, and how it changed through time. Some of these important traces are more than 3 billion years old, meaning they belong to a very early period in Martian history, when the planet was much younger than it is now. That span of time is almost beyond the scale of human understanding. But we can think of it more simply. Many signs of water on Mars have existed since a time when Earth itself was still very young. This gives the story greater depth. Water on Mars was not merely a late and brief event that appeared and disappeared recently. It was part of the planet's ancient history, written deeply into its shape from its earliest ages. As a rover moves across the red ground and points its cameras ahead, it sometimes reveals soft curves in the landscape that the human eye can easily associate with a dried river. No water remains there. There is no sound of flowing currents, and no surface rippling beneath the wind. Yet the form of the rocks and soil still preserves the memory of ancient motion. A low bank here, a curved channel there, a broad region spreading outward like a place where sediment once emptied into still water. The feeling is remarkable. It is like seeing the footprints of something that left long ago, yet finding those footprints too clear to ignore. Science, of course, does not rely only on visual resemblance. Researchers do not see a curved feature and immediately declare that it was a river. They compare Martian terrain with landforms known on Earth. They measure slopes, grain sizes, the arrangement of rock layers, mineral composition, and the surrounding geological context. It is the combination of many different forms of evidence that makes the story of water on Mars convincing. A single valley may raise questions, but when that valley appears alongside branching channels, layered sediments, ancient deltas, and minerals formed in watery environments, the larger picture becomes far clearer. Perhaps the most striking part of this story is the contrast. Present-day Mars can hardly preserve stable liquid water at its surface. Yet the same planet carries so many signs that water once played a role powerful enough to shape entire landscapes. Water may have eroded rock, carried material across great distances, deposited it in layers, and left forms that human beings can still recognize billions of years later. This means water did not simply pass through in a shallow, fleeting way. In at least some locations, and during at least some periods, it remained long enough to leave a true and lasting mark. When imagining ancient Mars, we do not need to picture a green planet like Earth, covered in vast oceans and forests. The evidence may allow for something more modest, but still extraordinary. Seasonal or longer-lasting streams, ancient lakes within impact craters, wetter surfaces, and intervals when liquid water could remain long enough to alter rocks and soil. That alone is enough to transform the way we see the red planet. Its dryness today does not close the story. It makes the story deeper. Every dry river channel, ancient delta, sedimentary layer, and mineral formed in the presence of water is like a message from the past. Together, they show that Mars was once different. It may not have been as gentle as Earth, but it was certainly not identical to the cold desert we see now. From these remaining traces of water, a clear idea begins to take shape. If rivers once flowed and lakes once existed, if sediments and minerals formed through the presence of water, then the Martian atmosphere must also have been different. It was likely thicker and more stable, capable of retaining more heat and providing the pressure liquid water needed. These marks do not tell only the story of water. They quietly point toward a lost sky and toward the conditions that once surrounded and supported the red planet. On Earth, water is so familiar that we often forget how many conditions must come together for a river to flow, a lake to remain still, or rain to fall and soak into the ground. Water needs more than a temperature warm enough to keep it from freezing and cool enough to prevent it from evaporating too quickly. It also needs an atmosphere thick enough to press gently but steadily against the surface. That pressure is called atmospheric pressure, and although we cannot see it, it helps liquid water remain in rivers, lakes, oceans, and even the small puddles left behind after rain. Mars today no longer has the conditions needed for liquid water to remain on the surface as it does on Earth. An atmosphere still surrounds the planet, but it is far too thin, like a protective covering that has weakened greatly over a very long time. Beneath that fragile sky, the ground is cold, the air is dry, and nearly everything seems to push water away from its familiar liquid state. If a drop of water appeared there, it would have very little time to rest, spread outward, or begin to flow. It could quickly freeze, evaporate, or leave the liquid state before it had time to create any clear mark. On Earth, we rarely think about atmospheric pressure because it is always quietly present around us. The air presses gently on the ground, the oceans, and every puddle left after a storm, helping water remain stable as a liquid. At high elevations, where the air is thinner, water boils at a lower temperature. That small difference shows how strongly the state of water depends on the atmosphere above it. Mars carries this principle to a far more extreme level. The air there is so thin that liquid water has almost no lasting place on the surface. The cold makes this fragility even more apparent. Mars receives less sunlight than Earth, and its thin atmosphere cannot hold warmth for long. A stretch of ground may warm during the day, but as the light fades, the heat quickly escapes. The rocks become cold again. The dust becomes cold again. A surface that briefly held a little warmth sinks once more into the deep Martian night. In such an environment, water cannot quietly gather into lakes, flow steadily through valleys, or maintain the familiar cycle of rain, rivers, and oceans that we know on Earth. The places that may once have held water are now filled only with rock, soil, and dust. Ancient riverbeds no longer carry flowing water. Depressions no longer hold lakes reflecting the light. Sedimentary layers once arranged by water now rest motionless beneath the cold sky, like old pages that have lost the movement that once gave them life. The present environment has not erased every memory of water, but it no longer allows water to continue existing in the same way. This makes Mars even more remarkable. The planet is not entirely without water. Water may still remain as ice at the poles, beneath the ground, or trapped within rocks and minerals. But liquid water at the surface, the kind that can create rivers and lakes as it does on Earth, is almost completely incompatible with present conditions. Water has changed its shelter, changed its form, and withdrawn from the red surface like a presence that remained for a very long time before quietly disappearing. This is why the ancient signs of water on Mars matter so much. Dry river channels, old deltas, and rock layers formed in watery environments do more than show that water once passed through. They suggest a different Mars, one whose atmosphere may once have been thicker, whose pressure may have been greater, and whose temperatures may have remained more stable during certain ancient periods. It was not necessarily a second Earth, but there may have been times when the red planet was different enough from today for water to remain longer, travel farther, and carve features into the ground that can still be seen now. Mars today shows us a world where liquid water can no longer remain easily at the surface. Yet that very absence makes the past stand out more clearly. The vanished streams no longer flow, and the ancient lakes no longer shine beneath the sun. But their traces remain in the terrain, the rocks, and the wide, dry landscapes. From a single drop of water, unable to remain beneath the Martian sky today, we begin to glimpse the outline of another sky in the distant past. A sky that may once have been thick enough to hold water, even if only during the earliest ages of the red planet. If we looked only at Mars as it is today, it would be easy to believe that the planet had always been this way. Cold, dry, silent, covered in red dust, with almost nowhere gentle enough for liquid water to remain on the ground for long. But a planet has a youth of its own. It too passes through periods that are more violent, warmer, and more chaotic, when its interior still holds more heat. Its sky has not yet become as thin as it is now, and time has not yet dried the surface until almost everything has faded into memory. Mars formed about 4.5 billion years ago, around the same time as the other large and small planets of the solar system. Back then, nothing was as settled as it is today. Fragments of matter were still colliding. Young celestial bodies remained hot. In many places, surfaces may have melted and then cooled again as planetary crusts gradually hardened into rock. Earth also passed through a youth like this. Mars did as well. It did not begin with the stillness we see in modern images. It began within a solar system filled with impacts, heat, and motion, like a world trying to take shape amid the distant noise of time. During that ancient period, the interior of Mars may have been far more active than it is today. Volcanoes erupted, gases escaped from inside the planet, and dust and water vapor may have been released into the atmosphere. The enormous volcanoes of Mars, including Olympus Mons, which later became the largest volcano known in the solar system, show that the planet was not always quiet. It once possessed tremendous internal energy. Lava flows moved across the surface, covering immense regions before cooling beneath a sky very different from the Martian sky of today. The atmosphere may also have been thicker. We should not immediately imagine a green Mars resembling Earth, covered in forests, vast oceans, and rain-filled clouds. That picture could easily lead the story in the wrong direction. But compared with the present, young Mars may have been more effectively sheltered. A thicker atmosphere would have created greater surface pressure, and with higher pressure, liquid water would have had a better chance of remaining stable. It would not have disappeared as quickly as it does under the cold, dry, low-pressure conditions of today. There may have been certain periods, regions, or seasons when liquid water flowed across the surface long enough to leave lasting traces. Those traces still remain on Mars, even though water withdrew from the story long ago. From orbit, observers can see ancient valleys, winding channels, depressions resembling lakebeds, and places where sediments were once deposited in layers. Many of these signs of ancient water are between 3 and 4 billion years old. That age is almost impossible to grasp on the scale of a human life. But within planetary history, these features are like surviving early pages from a book blurred by wind and dust. On those pages, Mars does not appear as a lifeless desert from the very beginning. It appears as a world across which water once moved. Shallow lakes may once have rested inside impact craters. They were not necessarily broad seas like those on Earth, but low, cold bodies of water that may have appeared and disappeared as the climate changed. At certain times, ice may have melted, or temporarily warmer conditions may have released water. It could have flowed down slopes, gathered in low-lying basins, and carried sand, mud, and minerals along the way. The lake surfaces may not have remained calm for long. They might have frozen during colder periods, evaporated as the air became drier, or gradually disappeared beneath accumulating dust. Yet if they endured long enough, water could perform its familiar work, wearing down rock, transporting material, and leaving behind curved channels, shorelines, and layers of sediment. A stream does not need to be large to write its story into stone. On Earth, even a small creek flowing through many seasons can cut into the soil, carry gravel downhill, and soften the sharp edges of rock. On ancient Mars, if water once flowed seasonally, appeared after temporary warming events, or moved down from higher ground into lower basins, it could have created the features that orbiting spacecraft observe today. What makes these marks so remarkable is that they remain on a world now almost completely unable to support stable liquid water at the surface. Every dry Martian valley, therefore, feels like a question repeated across billions of years. How different was the sky above it then? The Martian sky may once have held thin clouds. It was probably not a blue, moisture-rich sky like Earth's, but an atmosphere thicker than today's, containing dust, volcanic gases, and perhaps water vapor suspended in the air from time to time. Sunlight on Mars has always been weaker because the planet lies farther from the sun than Earth does. And in the distant past, the young sun itself was dimmer than it is today. This means that the presence of liquid water on early Mars cannot be explained by a simple story. Perhaps a thicker atmosphere retained part of the planet's warmth. Perhaps episodes of volcanic activity changed the climate for a time, releasing additional gases and heat into the environment. Large asteroid impacts may also have created brief warmer periods when surface ice melted and water flowed through valleys. Ancient Mars, therefore, did not necessarily need to remain warm for long stretches in the way Earth does. It may have entered gentler periods only occasionally, long enough for liquid water to appear, move across the ground, and leave its marks in the rocks before the planet became cold and dry once again. It is precisely this uncertainty that makes Mars so compelling. A simple version of the story would say that the planet once resembled Earth and then lost everything. Science, however, is usually more cautious. Ancient Mars may have been warmer and wetter than it is today, but that does not mean it was ever a second Earth. It may have been a world somewhere between two states, not as completely cold and dry as it is now, but not as stable or fertile as our own planet. Water may once have been present, though perhaps not always in abundance. The climate may have been gentler at times, yet still cold, still harsh, and still dependent on changing periods and conditions. Let us look more slowly at an ancient landscape on Mars. Before us lies a broad basin, its crater walls worn down by time. In the distance, dry channels curve downward from higher ground. Across the floor, layers of sediment rest one above another like thin pages of paper. At some unimaginably distant time, water may have flowed into this place. It carried fine dust and small fragments of rock, then allowed them to settle. A colder season arrived, and the surface of the water froze or began to shrink. Another season returned, and the flow carried in more material. There were no loud waves, no forests along the shore, and no animals moving through the scene to make it feel familiar to human eyes. There were only rock, water, cold air, and time. For a planet, however, that would already have been a great deal. Wherever liquid water exists, chemical reactions have more opportunities to take place. Minerals change when they come into contact with water. Rocks are altered. New layers of material are created. So when spacecraft discover signs of clay, mineral salts, or ancient sediments, they are not merely finding different types of rock. They are finding evidence of an environment that was once different. Clay, for example, often suggests that water remained long enough to interact with rock and gradually change it. It is like a stain left behind after the water has gone. Quiet, but enduring. Younger Mars probably did not have only one face. Some regions may have remained cold and dry for long periods. Ice may have rested beneath the surface in others. Water may have flowed briefly in one place and then disappeared. Some regions may once have held lakes. Others were covered by volcanic material. In certain places, asteroid impacts shattered the ground, creating new terrain that later guided water downhill. The planet was not a simple picture. It was a collection of many different landscapes, changing with time, elevation, climate, and disturbances from both within and beyond the planet. The contrast becomes even clearer when compared with Mars today. The present atmosphere is so thin that liquid water can hardly remain stable on the surface. Low temperatures make ice a more stable form. The dry air draws water vapor away. Dust settles over rocks, winds cross empty plains, and ancient riverbeds remain only as silent shapes. Yet if we move backward by billions of years, those dry channels may once have been wet. Empty lakebeds may have reflected the pale sunlight. Sedimentary layers may have settled through water rather than being shaped only by wind. What makes the past of Mars feel both beautiful and sad is that it has not disappeared completely. It remains within the landscape. On Earth, a river that dries up may later be covered by vegetation, crossed by roads, or erased by new rainfall. On Mars, where change often happens more slowly and the landscape is not constantly disturbed by life, ancient features can survive for immense spans of time. Billions of years later, human beings can still see them from far away. Not with the naked eye, but through orbiting spacecraft, cameras, mineral-detecting instruments, and robots moving across the rocks. We read a vanished world through the curves preserved in its ground. Perhaps, on some unimaginably distant morning, if we could stand on ancient Mars, the horizon would not seem quite as harsh as it does now. The sunlight would still be pale because the sun was farther away. The air might still feel cold. But in a low basin, a shallow body of water could be resting beneath thin clouds. The wind might move across it, creating small ripples. Red dust would cling to the shore. Dark volcanic rocks might lie among layers of fine mud. There would be no birdsong, no plants, and none of the familiar breath of Earth. There would only be a younger planet holding water on its surface a little longer before everything gradually changed. Then time passed. The atmosphere slowly thinned. Heat within the planet weakened. The conditions that once allowed water to remain became increasingly rare. Lakes dried up. Streams stopped flowing. Ice and dust replaced open water. Places that may once have been wetter gradually became dry landscapes. Mars did not transform in a single day, nor did it lose its past in one sudden moment. The planet changed over millions, hundreds of millions, and eventually billions of years. The process was so slow that no observer standing there could have witnessed it in a single glance. Yet across the full scale of its history, the transformation was immense, from a world that may once have been wetter than it is today to the cold, dry planet we are now exploring. This contrast is also what makes Mars feel more familiar to us. It is not merely a red point in the sky, nor only an empty place where human beings dream of walking someday. It is a planet with memory. That memory is not written in words, but in dry riverbeds, minerals, ancient lake floors, and layers of soil resting one upon another. Every trace of water on Mars is like a surviving fragment from the planet's youth, when the surface had not yet become as dry as it is now, when the sky may have been thicker, and when liquid water had the chance to touch the rocks and remain long enough to change them. Seen in this way, the present state of Mars no longer stands alone. Today's cold carries the shadow of a warmer past. Today's dryness carries the shadow of vanished flows. Today's silence carries the shadow of an age when the planet was more active, when volcanoes still shaped the surface, when the atmosphere was thicker, and when water moved through environments that no longer exist. Younger Mars does not need to have resembled Earth to be important. It only needs to have been different, to have experienced gentler conditions at certain times, and to have allowed liquid water to appear during some periods. That alone gives its story enough depth to make us want to listen. A cold and dry planet was not necessarily always cold and dry. Some worlds have changed so profoundly that their present appearance is only the final outer layer of a very long story. Mars is one of those worlds. And when we look across its red plains today, perhaps the most important thing to remember is that beneath the silent dust, traces still remain of a younger, more powerful Mars, one that may once have been far wetter than the lonely world we see now. The dry riverbeds, ancient lake floors, and layered sediments preserved on Mars tell us more than a story about water. They also tell us about a sky that was once different. Water, whether it is only a thin stream moving through a valley or a shallow lake resting inside a basin, cannot exist separately from the air surrounding it. For a planet to preserve liquid water on its surface, it needs more than melting ice and low-lying terrain. It needs an atmosphere thick enough to create pressure, retain some warmth, and give water time to remain before it disappears. Mars no longer has those conditions today. Its present atmosphere is extremely thin, so light that the surface is almost directly exposed to the cold of space. If liquid water appeared there, it would enter an environment far too harsh for it to remain stable. Low pressure makes it difficult for water to stay liquid. Cold temperatures pull it toward ice. The dry, thin air allows it to evaporate easily. Water on present-day Mars is therefore like a visitor arriving in a place with no shelter, drawn away by the surrounding environment almost as soon as it appears. Yet the ancient traces preserved on the ground suggest a Mars that was not always like this. If water once flowed long enough to carve into rock, if lakes remained long enough for sand and mud to settle, and if minerals formed through prolonged contact between water and stone, then the atmosphere above that planet was very likely thicker than it is now. It did not have to resemble Earth's atmosphere. It did not have to be warm enough to create blue oceans or long periods of rainfall. But it may have been heavier, deeper, and better able to preserve gentler conditions during certain periods. A thicker atmosphere would first have changed the pressure at the surface. For water, pressure is extremely important, even though we cannot see it. On Earth, we live beneath a layer of air heavy enough for water to remain in ponds and lakes, flow through rivers, and collect after rain without immediately disappearing. We are so accustomed to this that liquid water seems like its most natural state. But on worlds with atmospheres that are too thin, water is not supported in the same way. There is not enough atmospheric pressure to help it remain stable. So if ancient Mars once had liquid water on the ground, its atmosphere must have created conditions more favorable than those of today. A thicker atmosphere may also have helped the planet hold onto heat more effectively. Mars lies farther from the Sun than Earth, so the sunlight and warmth it receives have always been weaker. In the distant past, the young Sun was dimmer than it is today, making it even more difficult for liquid water to remain on Mars. If there were periods when water flowed, the planet needed some mechanism to make the surface less cold at certain times. A thicker atmosphere containing more heat-trapping gases may have acted like a thin blanket around the planet. That blanket would not have turned Mars into Earth, but it may have made the cold less absolute. And sometimes, even a small reduction in harshness can make an enormous difference. The ancient Martian sky may not have been clear or blue. It may have appeared dusty and pale yellow, reddish brown, or cold gray, depending on the amount of dust and the composition of the atmosphere at the time. Sunlight passing through the thicker air may have been softened by fine particles and tiny crystals of ice within the clouds. High above, thin clouds may have drifted slowly across a sky unlike any morning on Earth. Below, red rock, dark volcanic stone, and ancient basins would have rested beneath the weak light. There would have been no forests, no fields, and no loud sound of flowing water like those of a living world. Yet in some places, water may still have moved across the ground, quietly and more persistently than present-day Mars allows. Imagine a low-lying region on ancient Mars. It may have been an impact basin, its crater walls gradually worn down over time, with small channels leading downward from higher ground in the distance. During a favorable period, ice may have melted, or water may have flowed in from somewhere else and gathered into a shallow lake. The lake did not need to be large. Its water may have been cold, cloudy, and mixed with dust and minerals. But with higher pressure and a thicker atmosphere, it would not have disappeared immediately. It would have had time to remain. Fine particles would have settled to the bottom. Minerals would have begun to change through contact with water. A thin layer of sediment would have formed, perhaps later covered by another layer. Those conditions may not have lasted forever. Lakes may have dried up. Streams may have stopped flowing. Colder seasons may have turned water back into ice. The climate may have changed, transforming once damp regions into dry ground. But the important thing to remember is that water did not need to remain forever in order to leave a mark. It only needed to return many times, or remain long enough during certain periods to alter the planet's surface. Rocks were worn down. Material was transported. Mud and sand settled into layers. Added together across immense spans of time, these small changes became the features that human beings can now read from orbit and through the eyes of robotic explorers. A thicker atmosphere in the past is therefore not an isolated idea. It is directly connected to what we see on the ground. An ancient river channel is more than evidence of flowing water. It is also indirect evidence of a sky that was once different enough for that water to exist. An ancient lakebed does more than tell us that water once gathered in a depression. It suggests that pressure, temperature, and climate occasionally allowed the water to remain. A layer of clay or a mineral formed in water tells more than the story of rock. It also tells the story of the environment surrounding that rock, of air, warmth, pressure, and time. Even so, we should picture ancient Mars with care. A thicker atmosphere does not mean the planet was ever as comfortable as Earth. It may still have been cold. It may still have remained dry for much of the time. Water may have appeared only during certain seasons, in particular regions, or after unusual events such as volcanic eruptions, climatic shifts, or major impacts that warmed the surface for a while. Mars may not have been a lost green world, but a red world that occasionally opened brief windows for water. Those windows alone were enough to write a very deep history into the rocks. Scientists are still trying to understand how thick the ancient Martian atmosphere may have been. This is a difficult question because that atmosphere changed over billions of years. What remains today is only a very thin fragment of the past. To reconstruct its earlier form, researchers must combine many different clues. Landforms shaped by water, minerals that form only under watery conditions, sediments preserved inside craters, the composition of the present atmosphere, and chemical traces still held within rocks. Each clue is like a small piece of a shattered vessel. No single fragment can tell the entire story, but when the pieces are placed near one another, the past begins to take shape. That shape is not yet completely clear. The Martian atmosphere may once have been far thicker than it is today, or it may have thickened only during certain periods, when volcanic activity released additional gases into the air, or when the planet's climate changed temporarily. Water may have remained in shallow lakes longer than we currently imagine, or many flows may have appeared only briefly before vanishing again. What is more certain is that present-day Mars is too cold and its atmosphere too thin to explain all of the ancient evidence of water easily. A thicker atmosphere, therefore, becomes an almost essential part of any picture of the planet's past. It was like the background light in an old room. We may notice the table, the walls, or scratches on the floor, but without light, none of those details would be easy to see. On Mars, the ancient atmosphere played that background role. It is not the most obvious feature in images of river channels or lakebeds, yet it quietly allowed those scenes to exist. It gave water a chance to touch the rocks. It allowed flowing water to carry material farther. It gave lakes time to deposit thin layers of mud. It gave the planet's surface time to remember. If we could stand on Mars during one of those favorable ancient periods, we might not see a warm world. The air might still feel cold so far from the sun. Wines might still carry red dust across empty plains. But the sky above would not feel as light and empty as it does today. It would have greater depth. It would carry more weight. The sunlight passing through it might appear softer and more clouded. In a low basin, shallow water might reflect the unfamiliar color of the sky. Along the shore, wet sand and mud would lie among volcanic rocks. The landscape would remain silent, but it would not be the completely dry silence of present-day Mars. It would be the silence of a planet still preserving some of the conditions water needed to exist. Then, those conditions gradually changed, not in a single day, and not because of one simple event, but across such long spans of time that every part of the transformation seems to slow almost beyond perception. The atmosphere that had once been thicker began to thin. Surface pressure fell. Warmth became more difficult to preserve. Shallow lakes gradually dried up. Flowing water appeared less often. Ice and dust replaced open water. Regions that once had opportunities to remain wetter became dry land. The sky slowly lost its weight, and as it became lighter, water also lost its place on the surface. So when we speak of a thicker atmosphere in the past, we are not merely describing a lost layer of air. We are describing the underlying condition that once supported the entire story of water on Mars. Without it, ancient lakes would have struggled to remain for long. Without it, flowing water would have had difficulty traveling far. Without it, liquid water would have had almost no time to write the marks into rock that we can still read today. That atmosphere may not have transformed Mars into a second Earth, but it may have made the red planet less severe during the most important periods of its youth. From here, the Martian past begins to open into a quieter story. If the planet once had a thicker sky, greater pressure, and a better ability to retain warmth, then losing those things could not have been a minor change. A world does not simply let its atmosphere fall away without leaving traces. To understand why Mars became the cold, dry, fragile planet we see today, we must continue following that layer of air. From the days when it was still heavy enough to support water to the long period when it was gradually drawn away from the planet and dispersed into the vastness of space. A thicker sky does not simply disappear because time passes. For a planet to gradually lose its atmosphere, deeper causes must be at work within the planet itself. In the case of Mars, One of the earliest causes is not found in the sky or in the dry riverbeds across the surface, but in the planet's size. Mars is much smaller than Earth, and that small size influenced almost every part of its fate. When we look at Mars in the night sky, we see only a faint red point of light. In images taken by spacecraft, however, we see a world with enormous volcanoes, long canyons, broad plains, and impact craters scattered across the surface. These landscapes can make Mars seem very large, but when it is placed beside Earth, the difference becomes immediately clear. Mars is only about half Earth's diameter. It is a true planet with a crust, mountains, valleys, polar ice caps, and a geological history of its own, yet it is still a much smaller world than the one we live on. Size is more than a number on an astronomical chart. For a planet, size influences many things: how much internal heat it can retain, how strong its gravity becomes, how long geological activity can continue, and how effectively it can hold onto an atmosphere. In general, the larger and more massive a planet is, the stronger its gravity tends to be. That gravity is like an invisible hand holding everything close to the planet. The rocks on the ground, ice at the poles, water, if any is present, and the atmosphere surrounding it. Earth has a stronger hand. Its gravity is powerful enough to hold onto a thick atmosphere across immense spans of time. The air does not remain close to the ground by accident. It is held there by the planet's gravitational pull. Gas molecules are always moving and colliding, naturally tending to spread outward into space, but gravity draws them back and keeps them around Earth like a soft outer covering. Because of this, our atmosphere remains thick enough to create pressure, retain heat, transport water, vapor, form clouds and rain, and allow liquid water to remain stable at the surface. Mars is different. Its surface gravity is only about 38% as strong as Earth's. If someone could stand on Mars in a protective suit, they would feel much lighter. Everything would still be pulled toward the ground, but the hand holding it there would not be as strong as it is on Earth. For rocks and dust, that pull is still enough to keep them on the surface. But for an atmosphere, especially across billions of years, the weaker gravity becomes a serious disadvantage. An atmosphere is not a solid shell wrapped around a planet. It is made of countless gas molecules in constant motion. Near the surface, they are packed more closely together. Higher up, they become thinner and more widely separated, making them easier to affect by sunlight, the solar wind, high-energy collisions, and many other processes. If a planet has strong gravity, it has a better chance of pulling those molecules back and keeping them nearby. If its gravity is weaker, some gas in the upper atmosphere can escape more easily, especially when energized by the sun. On Mars, this loss did not happen in a single moment. But over millions and then billions of years, the gradual escape of even small amounts was enough to make the sky much thinner. We can imagine the atmosphere as a thin cloth draped over a sphere. If the hand holding the sphere is strong, the cloth is harder for the wind to pull away. If the grip is weaker, the edges of the cloth are easier to lift and carry off piece by piece. Mars did not lose its entire atmosphere all at once. It faded gradually, so slowly that no single day on the planet could ever be called the day the sky disappeared. But on the time scale of a planet, the difference between a strong hand and a weak one can determine the future of an entire world. This helps explain why ancient Mars, even if it once had a thicker atmosphere, struggled to preserve it forever. A denser layer of air may once have surrounded the young planet. Volcanoes may have released gases into the atmosphere. Asteroid impacts, internal activity, water vapor, and carbon dioxide may all have helped make the Martian sky heavier than it is today. But preserving that atmosphere for billions of years required gravity strong enough to hold it and a protective system durable enough to defend it. Mars may have had the beginning of that story, but it probably did not have the conditions needed to keep it for very long. Mars's smaller size also affected something deeper: the heat inside the planet. A smaller object usually cools more quickly than a larger one. We can see this in everyday life. A small stone heats up quickly and cools quickly as well. A large block of rock holds heat for longer. A small bowl of soup cools faster than a large pot. The same principle applies to planets, though the process unfolds across billions of years. Earth is larger and contains more material, so its interior has retained heat for longer. Mars is smaller, so it lost its internal heat more quickly. When a planet is young, its interior is hotter. That heat does not simply remain still. It drives motion deep within the planet, causing hot material to rise and cooler material to sink. It fuels volcanic activity, reshapes the crust, and on some worlds helps sustain important processes within the core. A planet with abundant internal heat is like a body that is still warm, still moving, and still capable of renewing parts of its surface and atmosphere. Volcanoes can release gases. The crust can continue to change. Energy from within remains part of the story unfolding above. But when a smaller planet cools more quickly, those activities also weaken sooner. Mars once had enormous volcanoes and vast regions covered by lava. This shows that it was not a dead world from the beginning. It once possessed powerful internal energy. It erupted, and it brought material from deep inside the planet to the surface. Over time, however, its smaller size allowed that internal heat to escape more quickly than Earth's. As the heat declined, volcanic activity became less frequent. As the volcanoes weakened, less new gas was added to the atmosphere. Meanwhile, the processes carrying atmospheric gases away into space continued. For an atmosphere to survive over long periods, it must do more than remain trapped around a planet. It must also be replenished. On a geologically active world, volcanoes and other processes can return gases to the atmosphere. If some gas is lost, the planet still has a chance to replace it. But when the interior cools, volcanoes become quiet, and deep planetary activity weakens, the atmosphere begins to resemble a leaking lake whose incoming streams are slowly drying up. At first, the change may be difficult to notice, but over enough time, the water level falls. On Mars, that falling lake was the sky itself. The planet's small size, therefore, did more than weaken its gravity. It also caused Mars to lose internal heat more quickly, allowing the processes within it to settle down sooner. Together, these two effects pulled the planet in an unfavorable direction. On one side, its gravitational hand was not as strong as Earth's and could not hold atmospheric gases as securely across billions of years. On the other, the planet's interior gradually cooled, weakening its ability to replace the gases that were lost. When gas escaped faster than it could be restored, the atmosphere could not preserve its original thickness forever. The difference between Earth and Mars is therefore not only a matter of their positions in the solar system. Earth lies closer to the Sun and receives more energy, but just as importantly, it is larger and more massive. It has stronger gravity to hold onto its atmosphere. Its interior has remained active for much longer. It has geological processes that allow the surface and atmosphere to continue interacting. Mars lies farther away, is smaller and lighter, and cooled more quickly. None of these differences explains the entire story by itself, but together they placed two once similar planets on very different paths. It is important to remember that Mars is not so small that it has no atmosphere at all. It still has air, winds, thin clouds, and enormous dust storms that can sometimes spread across nearly the entire planet. But its atmosphere is extremely thin compared with Earth's. It is like the surviving remains of a coat that was once much thicker. It is still there, still surrounding the planet, but it is no longer heavy enough to keep liquid water on the surface for long. It is no longer warm enough to soften the deep cold of the night. It no longer creates enough pressure to maintain the kind of stable environment that may once have existed during certain periods of the planet's past. If we return to the image of ancient Mars, we can imagine this loss unfolding very slowly. At first, the sky may have been thicker. Shallow lakes may have appeared. Some streams may have carved their way across the ground. Volcanoes were still active, releasing gases from inside the planet into the atmosphere. But beneath the crust, the small world was gradually cooling. Deep movements weakened. Its gravity remained less powerful than Earth's. In the upper atmosphere, individual gas molecules were struck by energy from the sun. Some escaped the planet's grasp and drifted away into space. There was no violent spectacle that an observer could watch with the naked eye. There was only a steady, silent loss accumulating across time. Eventually, flowing water became less common. Shallow lakes became more difficult to preserve. Ice began to play a greater role than liquid water. Dust settled over places that had once been wet. The atmosphere remained, but it had grown lighter than before. Mars did not become cold and dry only because it was small, but its small size made that path easier to follow. It was like a lamp with less oil, burning brightly in its youth and fading sooner than a larger flame. As the energy within weakened, the surface gradually lost the conditions that had once allowed water to remain. Seen in this way, the size of Mars is no longer a dry scientific detail. It becomes part of the planet's fate. Half Earth's diameter, only about 38% of Earth's surface gravity, and an interior that cooled more quickly. These numbers do more than sit inside textbooks. They help explain why the Martian sky was difficult to preserve, why water could not remain for long, and why a planet carrying signs of a wetter past gradually became a cold, dry world. They show that sometimes the difference between a planet that preserves its vitality and one that loses most of its atmosphere begins with the size of the world itself. But size is only one part of the story. Weaker gravity made it easier for gases to escape. Faster cooling caused geological activity to weaken sooner. And as we move deeper into the planet, we encounter another factor that may have been even more important: the Martian core. The interior of a planet does more than retain heat or feed volcanoes. It can also create an invisible shield around the world, protecting its atmosphere from streams of energetic particles released by the sun. On Earth, that shield is still active. On Mars, the story followed a quieter, sadder path, and perhaps a far more decisive one. Beneath the red dust, beneath the dry plains, ancient craters, and riverbeds that have been silent for a very long time, Mars once had a heart far hotter than it is today. That heart could not be seen from the outside, yet it quietly helped determine the fate of the entire planet. Whether the sky remained thick or became thin, whether volcanoes stayed active or fell silent, whether a magnetic field continued to protect the planet or weakened over time. All of these stories began, in part, deep within its interior. A planet is not born as a dead sphere of rock. In its youth, it is hot, unstable, and full of motion. Heat left over from its formation, from violent collisions during the early solar system, and from the decay of radioactive elements within the planet, keeps the interior from remaining still. Hot rock can move slowly. Material deep inside can separate into layers. A metallic core at the center may contain moving currents of electrically conductive material. These motions are not loud like storms at the surface, but across planetary timescales, they are far more powerful and important. Mars also passed through a youth like this. It was not always the cold, dry, dust-covered world we see today. In the distant past, its interior may still have been hot enough to support intense geological activity. Its enormous volcanoes, vast lava-covered regions, and signs of change across the surface show that the planet once possessed considerable internal energy. Heat rising from deep inside melted rock brought material to the surface and released gases from the interior into the atmosphere. When Mars was younger, it was not silent. It breathed through volcanoes, changed through lava, and held part of its energy deep within. But a small world cannot retain heat as long as a larger one. We can imagine this by placing a small cup of tea and a large teapot in the same cold room. The small cup will cool more quickly. It contains less water and less heat, and its exposed surface is larger in relation to the amount of liquid inside. The larger pot remains warm longer, not because it is somehow more remarkable, but because it contains more material to hold heat and loses that heat more slowly. The same is true for planets, except that instead of minutes or hours, the process unfolds across millions and billions of years. Mars is smaller than Earth, so in this comparison, it is more like the smaller cup. With a diameter only about half that of Earth, the entire planet contains less material capable of storing internal heat. Heat from deep within gradually moved outward and escaped into space. During the earliest periods, the difference may not have been very obvious. Mars was still hot enough, active enough, and violent enough to create enormous geological features. But as time passed, the advantage of a larger planet like Earth became clearer. Earth retained its heat for longer. Mars cooled more quickly. And when a planet cools, it is not only the surface that changes. Its deepest internal mechanisms also begin to weaken. As long as the interior remains hot, material can continue to move. These motions are somewhat like steam quietly rising within a pot of heating water. They may not always be easy to see, yet they constantly carry energy from warmer regions toward cooler ones. Deep inside a planet, hotter rock can rise very slowly, while cooler rock sinks just as slowly, creating deep currents known as convection. These movements can help sustain volcanic activity, reshape the crust, and give a planet a longer geological life. As the heat source weakens, everything begins to slow down. Volcanoes no longer erupt as often as they once did. Lava no longer finds its way to the surface as easily. Gases from the interior are no longer added to the atmosphere in the same amounts as during the planet's youth. Regions that were once highly active gradually become quiet. The surface continues to preserve evidence of a violent past, but beneath it, the engine slowly loses its heat. Mars did not shut down in a single moment. It cooled gradually, like glowing embers fading beneath a layer of ash. This had major consequences for the atmosphere. A planet may lose gases into space, but as long as its interior remains active, it still has a chance to replace some of them through volcanoes and other geological processes. Carbon dioxide, water vapor, and several other gases can escape from within the planet and help replenish the atmosphere. Earth has complex cycles that allow its atmosphere, oceans, rocks, and life to interact over immense spans of time. Mars was weaker in this respect. As its interior cooled, the supply of new gases also declined. Its atmosphere was already difficult to preserve because of weaker gravity, and it became even harder to restore once fewer gases were being released from within the planet. But the deepest effect of a cooling core was not limited to volcanoes. It was also connected to the magnetic field. On a planet like Earth, the global magnetic field is created by the movement of electrically conductive material within the liquid outer core. We can imagine that core as a region of hot, iron-rich metal moving slowly but continuously. When electrically conductive material moves under the right conditions, it can generate a magnetic field that surrounds the planet. This field cannot be seen with the eyes. It has no color and no clearly defined surface, yet it is one of Earth's most important protective layers. A magnetic field is like an invisible shield. It does not block everything, but it deflects many charged particles coming from the sun, helping prevent the atmosphere from being exposed too directly and too intensely over long periods. On Earth, this shield is still active. It surrounds the planet, stretches far into space, interacts with the solar wind, and creates phenomena such as auroras near the poles. Because Earth has a global magnetic field, its atmosphere is better protected from the constant stream of energetic particles flowing outward from the sun. Mars today does not have a strong global magnetic field like Earth. This does not mean that every trace of magnetism has disappeared. Some regions of ancient Martian rock still preserve localized magnetic fields, like fragments of memory frozen into the crust. These traces suggest that in the distant past, Mars may once have had a much stronger global magnetic field. In other words, the red planet may once have possessed an invisible shield of its own. But that shield was not maintained. The reason lies deep inside the planet. For a global magnetic field to survive for a long time, the planetary core must sustain the right kinds of movement in electrically conductive material. Those movements require energy, differences in temperature, and a core that remains sufficiently active. Because Mars is smaller and cooled more quickly, its internal engine may have weakened early. The core did not necessarily have to become completely solid, but the motions that once helped generate a global magnetic field may no longer have been strong or stable enough. As that process weakened, the global magnetic field declined as well. The image is quiet but immense. A young planet once had a hotter core, a stronger magnetic field, more active volcanoes, and a thicker atmosphere. Then, over time, heat escaped from the interior. Deep movement slowed. Volcanic activity became less frequent. The ability to replenish the atmosphere weakened. The magnetic shield also faded. There was no loud crack echoing through space. There was no single day that could be named as the moment Mars lost its protection. But across vast spans of time, the change produced a chain of consequences at the surface. As the global magnetic field weakened, the upper atmosphere became more exposed to the solar wind. The solar wind is a continuous stream of charged particles flowing outward from the sun into space, around a planet with a strong magnetic field. Many of those particles are redirected and do not sweep directly across the upper atmosphere in the same way. But when a planet gradually loses that shield, the upper atmosphere becomes more vulnerable. Individual gas molecules can receive energy, be pulled away, or be pushed farther from the planet. Over enough time, those small losses become enormous. What is especially striking is how closely every part of this story is connected. Mars is smaller, so its gravity is weaker. Because it is smaller, it also cooled more quickly. As it cooled, geological activity weakened sooner. As internal activity declined, the planet's ability to generate a global magnetic field also faded. As the magnetic field weakened, the atmosphere became more vulnerable to erosion by the sun. And as the atmosphere thinned, liquid water at the surface lost the conditions it needed to remain for long periods. From what seems like a simple difference in size, an entire chain of changes unfolded. Mars can be imagined as a house that once had a roof, walls, and a furnace inside. When the planet was young, that furnace burned more strongly. The thicker atmosphere was the roof. The magnetic field was the protective wall. Water may have appeared in some low, cold rooms, still partly sheltered from the outside. Then the furnace weakened. The protective wall began to fade. The roof was stripped away piece by the wind. The house remained standing, but its interior became colder, drier, and emptier. The remaining signs of water are like old stains on a stone floor, reminding us that this place once passed through a different age. Mars is, of course, far more complicated than a house, and many questions remain under investigation. What is the Martian core like today? How much of it is still liquid? When exactly did the process generating the magnetic field stop? Scientists continue exploring these questions through seismic data, magnetic traces preserved in rock, thermal models, and spacecraft observations. But the broader picture is already clear enough to reveal an important direction. The interior of Mars changed, and that transformation was deeply connected to the atmosphere the planet later lost. Seen from far away, the Martian surface appears motionless. Its enormous volcanoes still rise above the plains. Deep canyons still stretch across the planet. Ancient riverbeds remain silent beneath the dust. But the stillness at the surface does not mean the story began there. It began inside the planet, with heat that slowly faded, deep movement that weakened, and a core that could no longer maintain the same protection it had provided during Mars's youth. The surface is simply where the consequences are easiest to see. The cause often lies far below, hidden in deep darkness. And as that invisible shield weakened, Mars became more exposed to space. The upper atmosphere was no longer protected as it once had been. The solar wind could interact more strongly with the fragile layer of gas surrounding the planet. Following that process will help us understand more clearly why the Martian sky today remains only a thin, weakened covering above a cold and dry world. As the interior of Mars gradually cooled, it lost more than the heat that once powered its ancient volcanoes, or the ability to release fresh gases from deep within the planet into the sky. Something else also began to weaken, something far quieter, yet deeply important to the fate of the atmosphere. It was the planet's global magnetic field, an invisible layer of protection that may once have surrounded Mars during its distant youth. A magnetic field is not something we can see like clouds, water, or mountains. It has no color, no clearly defined shape, and it does not form a solid wall in space. But when a planet has a sufficiently strong magnetic field, its influence can extend far beyond the surface, like a wide umbrella opening into space. That umbrella cannot block everything, but it can redirect many charged particles arriving from the sun, reducing the direct impact on the upper atmosphere. Earth still has such an umbrella. Deep within our planet, hot, metal-rich, electrically conductive material continues to move through the liquid outer core. These motions generate a global magnetic field that surrounds Earth like an invisible shield. Because of this protection, many charged particles from the sun do not strike the atmosphere along the most direct path. Instead, they are redirected and guided along magnetic field lines. Near the polar regions, these interactions sometimes become visible as glowing curtains of aurora. That is the beauty we can see, but behind it lies a much deeper protective mechanism. Mars today no longer possesses a strong global magnetic field like Earth's. When scientists observe the red planet with instruments that measure magnetism, they do not find a single shield surrounding the entire world. Instead, they detect localized magnetic regions preserved within the crust, scattered unevenly like fragments of an ancient memory. These areas are not strong or connected enough to create a unified protective layer around the whole planet. Yet the magnetized rocks themselves reveal something important. Mars was not always as exposed as it is today. Rock can preserve a memory of a magnetic field. When molten lava cools, iron-bearing minerals within it may align themselves with the magnetic field that exists at that time. Once the rock hardens, that alignment can remain locked in place, like tiny compass needles trapped within the stone. Billions of years later, even after the global magnetic field has disappeared, ancient rocks may still preserve part of its signature. When spacecraft detect strongly magnetized regions in the Martian crust, they are reading an extremely old record, written during a time when the planet still possessed its own protective shield. There is a quiet beauty in this image. On the surface, present-day Mars is cold and dry. Dust covers the rocks, and winds move across empty plains. Yet within the ancient crust, some regions still preserve magnetic directions from a distant age. They are like pieces of charcoal that retain the faint warmth of a fire that has gone out. They are not enough to heat the room, but they are enough to prove that the flame once existed. The global magnetic field of Mars may have vanished long ago, but traces of it remain in the rocks, quietly reminding us that the planet was once better protected than it is today. When Mars still had a global magnetic field, its upper atmosphere was probably not exposed to space as directly as it is now. The sun sends more than light and warmth toward the planets. It also continuously releases a stream of charged particles known as the solar wind. This flow spreads throughout the solar system, passing planets and interacting with the magnetic fields, atmospheres, and surfaces of the worlds in its path. Around a planet with a magnetic shield, many of those particles are redirected. Around a planet that no longer possesses a strong global shield, the upper atmosphere becomes more vulnerable. We can imagine the magnetic field as a hand that does not touch the atmosphere directly, but changes the path of the things rushing toward it. If the atmosphere is a thin coat around the planet, then the magnetic field is like a protective buffer beyond that coat. It does not make a planet immortal. It cannot prevent every form of atmospheric loss. Even Earth allows a very small amount of gas to escape into space. But when a magnetic buffer is present, the atmosphere does not endure the full direct force of high-energy particles from space. Over billions of years, that difference can become enormous. For Mars, the story is not as simple as losing its magnetic field and immediately losing its atmosphere. Nature rarely works through one uncomplicated step. The Martian atmosphere was influenced by many factors at once. The planet's small size, its weaker gravity compared with Earth, the rapid cooling of its interior, declining geological activity, the decreasing supply of new gases, and the effects of the sun on the upper atmosphere. The loss of the magnetic field was not the only cause, but it made the planet more vulnerable to processes taking place in space. As the global magnetic shield weakened, the upper Martian atmosphere became like part of a roof that was no longer properly covered. The solar wind could interact more strongly with gas molecules at high altitudes. Charged particles from the sun transferred energy into the atmosphere, causing some atmospheric particles to move faster and contributing to processes that allowed them to escape gradually from the planet's gravity. A single molecule leaving did not create a visible disaster, but small losses continuing for long enough could transform an entire sky. Atmospheric loss is not like water pouring from a jar. It does not spill out once and then end. The atmosphere is eroded gradually from above, while the surface below continues to preserve traces of earlier periods. Ancient lakes dry out on the ground. Minerals in the rocks preserve evidence of water. Ancient magnetism in the crust preserves evidence of the lost shield. High above, the atmosphere continues to thin. These stories unfold in different layers of the planet, yet all of them lead toward the same result. Mars gradually became more exposed to space. During the planet's youth, when its core was still active enough to maintain a magnetic field, Mars may have experienced a period of greater protection. Its atmosphere may have been thicker, surface pressure may have been higher, and liquid water may have appeared in certain regions and during certain periods. A magnetic field does not create water, nor does it directly make an atmosphere thicker. But it can reduce the atmosphere's exposure to forces from outside, like someone sheltering a small candle from the wind. The candle still needs wax, a wick, and the right conditions to burn. But without protection from a strong wind, its flame will go out more quickly. This image helps us understand why a magnetic field matters. It was not the only character in the story of Mars, but it was a crucial layer of protection. While it remained, the red planet possessed another advantage. As it weakened, Mars lost part of its ability to resist erosion from space. Its gravity was already weaker than Earth's. Its interior also cooled more rapidly. Once the global magnetic shield was gone, the gradual thinning of the atmosphere becomes easier to understand. It was like a coat being pulled away from the outside while no longer being repaired from within. The magnetic traces preserved in Martian rocks are therefore more than dry scientific data. They are evidence that the planet once had a more dynamic past. Ancient rocks do not speak through sound, but they preserve the direction of a magnetic field that no longer exists. The localized magnetic regions scattered across the crust are like surviving pieces of a map showing a shield that once surrounded the planet. When scientists measure them, they are not merely studying rock. They are tracing the internal history of Mars, from the time when its core was active enough to generate an invisible shield to the period when that shield gradually disappeared. That disappearance also separated Mars from Earth in a profound way. Earth is fortunate not only because it has water or because it lies at a favorable distance from the sun. It is also fortunate because its interior remains active enough to sustain a global magnetic field. We live beneath a blue sky and rarely consider that part of its stability is protected by the movement of hot metal deep beneath our feet. Mars, although it may once have possessed conditions more similar to those of Earth than it does now, could not preserve that protection indefinitely. Once the global magnetic field weakened, Its atmosphere faced space in a far more direct way. From here, the image of Mars becomes both clearer and quieter. We no longer see only a planet smaller than Earth. We see a world that once had a hotter heart, an invisible shield, and a sky that may have been thicker, before gradually losing one advantage after another. What remains today is a thin atmosphere, isolated magnetic regions locked within the rocks, ancient riverbeds without water, and a red surface resting beneath the constant flow of particles from the sun. To understand how that atmosphere was eroded, however, we must turn toward the greatest external influence acting upon Mars. It was not a rare event or a storm that arrived and disappeared after a few days. It was the sun, the same star that illuminates every planet while continuously sending the solar wind outward into space. Earth's magnetic field still redirects much of that flow. On Mars, once the global shield had weakened, the solar wind became a quiet force of erosion, touching the upper atmosphere and helping draw the planet's ancient sky away from it, little by little. As Mars's global magnetic shield weakened, the red planet no longer faced space in the same way it once had. Its upper atmosphere became more exposed, more fragile, and more easily touched by forces that are always moving through the solar system. Among them was an invisible flow coming from the very star that had once warmed Mars, helped ice melt during favorable periods, and cast its light across shallow lakes and ancient river valleys. That star was the sun. We often think of the sun mainly as a source of light. Each day on Earth, it rises, slowly brightens the sky, warms the ground, and creates the familiar rhythms of day and night, warmer and colder seasons, life, and the daily patterns of living things. Seen this way, the sun resembles an enormous lamp at the center of the solar system, a distant sphere of fire sending light toward the planets. But the sun does more than shine. It also continuously releases a stream of tiny, fast-moving, electrically charged particles into space, traveling farther than the human imagination can easily follow. That stream of particles is called the solar wind. It is not wind in the same sense as wind on Earth. Terrestrial wind is moving air. We feel it against our skin, hear it passing through trees, and see it creating ripples across water. The solar wind is different. It is not air. It is a flow of charged particles, mainly extremely small particles such as protons and electrons, released from the sun's hot outer layers. They do not create a whistle like wind moving through a room. They do not shake leaves or bend grass. They move silently through space, yet they carry energy and electric charge, allowing them to interact with the magnetic fields and atmospheres of planets. We can imagine the sun as a distant flame, but not a flame that remains still. It gives off light while also breathing an invisible stream of matter into space. That material spreads in every direction, crossing the orbits of Mercury, Venus, Earth, and Mars before continuing much farther outward. The planets do not move through perfectly quiet space. They travel within this flow of particles, like stones resting in an extremely thin, immensely broad stream that cannot be seen with the naked eye. When the solar wind reaches Earth, it encounters our planet's global magnetic field. That field bends and redirects the incoming particles, preventing them from striking the atmosphere along the most direct path. Some energy still enters near the polar regions, creating curtains of aurora visible during cold nights in the far north or south. But most of Earth's atmosphere is not directly exposed to the full flow of those particles. It has a protective buffer beyond it, an invisible shield maintained by movement deep within the planet's core. Mars today does not possess such a strong global shield. The magnetic regions that remain within its crust are only isolated fragments of protection and do not surround the entire planet. As a result, when the solar wind reaches Mars, it can interact more directly with the upper atmosphere. This does not mean that the entire stream of particles strikes the ground. Mars still has an atmosphere, complex reactions still occur at high altitudes, and the planet has its own region where the atmosphere and solar wind interact. But compared with Earth, The red planet lacks a powerful global protective layer, leaving its upper atmosphere more vulnerable. The upper atmosphere is an extremely fragile region. The air there is not dense as it is near the surface. Gas molecules are more widely separated and more easily affected by outside energy. When ultraviolet light from the sun reaches them, or when charged particles from the solar wind interact with them, some molecules may be broken apart, ionized, or given additional energy. These high-altitude particles are already close to the boundary between the planet and space. If they are pushed strongly enough, they can overcome Mars's weaker gravity and leave the planet. This does not happen like a storm that strips away the entire sky in a single day. It is much slower and smaller, almost impossible to notice within a brief moment. One escaping particle does not change an entire planet. A single day of atmospheric loss does not turn Mars into a cold desert. But Mars has existed for billions of years. The sun never stops releasing the solar wind. The upper atmosphere never stops interacting with that flow. And when a small loss is repeated across an immense span of time, the sky can gradually become thinner. We might imagine a fine layer of dust resting on a table. If we blow across it once very gently, almost nothing seems to change. But if a weak current of air continues day after day, some of the dust will slowly be carried away. The process matters not because each moment is especially powerful, but because it never completely stops. The solar wind has acted upon Mars in much the same way. It did not need to destroy the planet. It only needed to touch the upper atmosphere, transfer energy, remove a small amount of gas, and continue doing so across timescales far longer than a human life. When Mars still possessed a stronger global magnetic field, more of the particles from the sun were probably redirected. The upper atmosphere was better protected, like a house sheltered from part of the rain and wind by a roof overhang. But as that protection weakened, charged particles from the sun could come closer, interact more strongly, and contribute to atmospheric erosion. This is an important point. The sun is not only a source of energy that can warm a planet, it is also a source of forces capable of gradually depleting a planet's atmosphere, especially when that planet is small, has weaker gravity, and lacks a protective magnetic field. This gives the sun a two-sided role in the story of Mars. On one side, sunlight is what warms the surface, allows ice to melt during favorable periods, and gives liquid water a chance to appear when pressure and climate conditions permit. On the other side, the sun also sends out a wind of charged particles, emits high-energy radiation, and interacts with the upper atmosphere. A star that sustains can also erode. A source of light can also be the source of an invisible wind. Throughout the solar system, planets live with both sides of that relationship. For Earth, the balance leans toward protection. Our planet is large enough to hold on to its atmosphere more effectively. Its gravity is stronger. Its interior remains active enough to maintain a global magnetic field. Its atmosphere is thick and divided into many layers. So, although Earth is still affected by the solar wind, it is not left exposed in the way Mars is today. Auroras on Earth show that this interaction still occurs, but they also remind us that the magnetic field is doing its work, guiding streams of charged particles along paths that are less damaging to most of the atmosphere. Mars exists in a far more fragile situation. It is smaller, its gravity is weaker, its interior cooled more quickly, and its global magnetic field faded long ago. Its present atmosphere is only a very thin layer of air compared with Earth's. Because of this, when the solar wind passes by, its interaction with the upper atmosphere becomes an important part of the story of atmospheric loss. It is not the only part, but it cannot be ignored. The process is like water flowing along the edge of soft soil. Each passing current removes only a little, but over time, the shoreline retreats. Spacecraft sent to Mars have helped scientists see this process more clearly. They have measured how the solar wind interacts with the upper atmosphere how gas particles can be carried away into space, and how powerful eruptions from the sun can temporarily increase the rate of atmospheric loss. These observations have turned a distant idea into a process that can be directly studied. Mars is not only a planet that lost water and atmosphere in the past, it is still losing part of its atmosphere to space today, even though the rate is very small compared with the size of the entire planet. That image makes Mars feel even quieter. On the ground, the red plains appear almost motionless. The craters do not visibly change before human eyes. Enormous volcanoes stand still as though they have been asleep for millions of years. But high above the surface, where the atmosphere gradually thins into space, an interaction is still continuing. Particles from the sun arrive. Gas molecules are disturbed. A tiny fraction escapes. There is no explosion, no great fracture, and no violent scene like those shown in movies. There is only a silent erosion, difficult to see but persistent. Mars today can be imagined as someone standing outside in the cold wearing only a very thin coat. In the past, that coat may have been thicker. There may also have been an outer windbreak. But the shield disappeared, the coat became thinner, and the wind from the sun has never stopped blowing. No single gust makes that person vanish, but each one makes it harder to hold on to warmth. For the red planet, that warmth means a thicker atmosphere, greater pressure, and conditions that allow liquid water to remain for longer periods. As those conditions gradually disappeared, the surface became colder, drier, and more distant from the image of a young Mars that once held water. The solar wind also reminds us that a planet's atmosphere does not depend only on the planet itself. It also depends on the surrounding space environment. A world may release gases through volcanoes, contain ice and water, and pass through favorable climatic periods. But if it cannot retain its gases against the influence of its parent star, its sky will change. A planet does not exist in isolation. It lives within the flowing environment of the solar system, exposed throughout its lifetime to sunlight, gravity, radiation, and streams of particles from the sun. For Mars, this combination led to a clear result. The upper atmosphere became especially vulnerable. Without a strong global magnetic field, Mars lacks the large shield that diverts most charged particles away from the planet, as Earth's field does. Without strong gravity, energized gas particles have a greater chance of escaping. Without a powerful and long-lasting supply of new gases from geological activity, what is lost is difficult to replace. No single factor tells the whole story, but together they help explain why the Martian sky gradually became thinner. At times, the sun is quieter, and the solar wind flows steadily like a constant background current. At other times, the sun becomes more active and releases larger bursts of particles and energy into space. When those disturbances reach Mars, the upper atmosphere may be affected more strongly for a time. Events like these are not the only reason Mars lost its atmosphere, but they resemble occasional powerful gusts striking a roof that has already become weak. No single gust explains the entire history, but across billions of years, they contribute to the overall erosion. It is important not to imagine the solar wind as a single enemy that stole the entire Martian atmosphere. The real story is more subtle. Mars lost gas through several causes working together. The planet is small, its gravity is weak, its core cooled quickly, its global magnetic field declined, geological activity weakened, and the solar wind continuously acted on the upper atmosphere. The sun is the largest external factor in this part of the story, but it became far more dangerous only after Mars had lost much of its ability to protect itself. Seen from a distance, the sun still appears as a gentle source of light in imagined views of Mars. Its light falls across the red plains, the craters, the polar ice caps, and the walls of deep canyons. But at the same time, an invisible stream of particles from that same star continues to pass over the planet. It does not need to be seen in order to be real. It does not need to make a sound in order to have an effect. It only needs to keep blowing, day after day, year after year, million years after million years. At the upper edge of the Martian atmosphere, where the air becomes so thin that it nearly dissolves into space, that stream of particles has left its mark. It has helped pull away part of the atmosphere. It has made an already thin sky even less able to grow thick again. And it connects the story inside the planet with the environment beyond it. The core cooled, the magnetic field weakened, and the solar wind began reaching the atmosphere more directly. At the upper edge of the Martian atmosphere, where the air becomes so thin that it nearly blends into space, the loss happens quietly. No crack opens across the sky. There is no single day when the entire atmosphere is swept away like a gigantic storm. What happened to Mars was much slower, much smaller, and far more persistent. The atmosphere of the red planet did not disappear in one moment. It leaked away gradually, particle by particle, through layers so thin and across spans of time so vast that the human imagination can barely grasp them. After Mars lost its strong global magnetic field, its upper atmosphere became more vulnerable to high-energy sunlight and the solar wind. The gas particles there were already extremely sparse, extremely light, and very close to space. They were not held as tightly as the air near the surface. They moved constantly, collided, gained energy, lost energy, and changed direction again. Most were still pulled back by gravity. But a very small fraction, under the right conditions, could reach enough speed to leave Mars forever. The planet's gravity can be imagined as an invisible hill. Every gas particle that wants to escape into space must climb over that hill. Slowly moving particles are like marbles rolling up the slope without enough energy to reach the top. They slow down, fall back, and remain around the planet. But lighter, faster particles, or particles given additional energy by sunlight and collisions in the upper atmosphere, may be able to cross the summit. Once they travel far enough beyond it, they do not return. They become part of space. Mars is at a disadvantage because its gravitational hill is lower than Earth's. Surface gravity is only about 38% of Earth's, so the planet is less able to hold on to gas, especially high in the atmosphere. This does not mean that every gas molecule can easily escape. Some atmosphere is still retained, which is why Mars still has air, winds, thin clouds, and dust storms today. But over billions of years, if even a very small amount of gas escapes continuously, the sky can become dramatically thinner. For a planet, a small loss that never stops can sometimes matter more than a violent event that lasts only a short time. Among the particles most able to escape, hydrogen plays a special role. Hydrogen is the lightest element. Because it is so light, it can move more quickly in the upper atmosphere. When water or other hydrogen-bearing molecules are broken apart by sunlight, hydrogen atoms can be released and rise higher. There, if they receive enough energy, they have a better chance of overcoming Mars's gravity than heavier elements do. This is why hydrogen is such an important clue in the long story of how Mars lost both atmosphere and water. Water does not need to flow in rivers and then visibly disappear in order to be lost. Part of the story takes place much higher above the surface. Water molecules can reach the upper atmosphere as water vapor. Sunlight, especially high-energy radiation, can split those molecules into hydrogen and oxygen. Hydrogen is lighter, faster, and more likely to escape into space. Oxygen is heavier and may remain longer, react with rocks, participate in other chemical processes, or be lost through different mechanisms of its own. Over immense spans of time, every small amount of hydrogen that leaves the planet represents another way in which ancient Martian water disappears from the surface record. This process is nothing like an ocean evaporating in a single day. It is more like a container left in sunlight with a tiny opening at the top. Over an hour, almost nothing seems to change. Over a day, the difference is still difficult to notice. But left for years, the amount of water declines. Mars has been standing beneath the sun for billions of years. The opening is not one single crack, but many different pathways of loss. Hydrogen escaping because it is so light, particles altered by radiation, and ions drawn away from the upper atmosphere by the solar wind. Ion may sound like a dry scientific term, but it simply means a particle that carries an electric charge. Under normal conditions, an atom or molecule may be electrically neutral, with no obvious net charge. But when high-energy sunlight from the sun or a powerful collision acts on it, an electron can be knocked away. The particle left behind becomes an ion. Once it carries a charge, it is no longer influenced only by gravity. It becomes much more responsive to electric fields, magnetic fields, and the stream of charged particles coming from the sun. In the upper atmosphere of Mars, this is extremely important. As the solar wind passes Mars, it carries charged particles and the interplanetary magnetic field with it. Gas particles that have already been ionized high in the atmosphere can be swept away through this interaction. They can be imagined as dry leaves lying along the edge of a road. Without wind, many of the leaves remain where they are. But when a breeze passes, the lightest leaves near the outer edge are more easily carried away. The upper atmosphere of Mars is much like that exposed edge. The ions are not buried deep within a thick layer of air, and they are not protected by a strong global magnetic field as they are on Earth, so they are more vulnerable to the stream of particles coming from the sun. Not every ion is swept away. Not every particle in the upper atmosphere escapes the planet. Atmospheric science is always more complicated than any simple image. Some particles fall back. Some collide with others and lose energy. Some follow complex paths around the planet. But what matters is that Mars has several conditions that make the escaped fraction significant over immense spans of time. Its gravity is weaker. Its global magnetic field is no longer strong. The upper atmosphere is more directly exposed to the solar wind, and the supply of new gases from inside the planet weakened as the core cooled and volcanic activity faded. The leakage of air is therefore not simply a matter of a few gas particles drifting away. It is a layered process. Some light atoms, such as hydrogen, escape more easily once they reach sufficient speed. Some particles are broken apart or heated by sunlight. Others become ions and are then pulled away by the solar wind. Some molecules in the upper atmosphere gain energy through collisions, begin moving faster, and eventually pass beyond the region where the planet can hold them. Each of these pathways is small when considered alone, but together, over billions of years, they have helped thin the Martian atmosphere. This also helps explain why atmospheric loss is not something easily seen from the surface. If someone stood on Mars for a single day, they would not see the air flowing upward into the sky. They would see only a pale red sky, weak sunlight, fine dust, wind moving past the rocks, and a deep sense of emptiness. The loss occurs too high above the surface, in air too thin, and on a scale too small for human eyes. It belongs to the boundary between atmosphere and space, where individual particles quietly follow paths that determine whether they remain or leave. Yet these nearly invisible processes become powerful when multiplied by time. A planet can lose only a tiny fraction of its atmosphere in a single year and appear almost unchanged. But after millions of years, the missing gas begins to matter. After billions of years, the sky can become entirely different. Shallow lakes that once had a chance to survive become harder to sustain. Streams that may once have crossed the valleys become increasingly rare. Liquid water loses the environment that supported it. The surface becomes colder and drier, and the ancient signs of water gradually become relics of a time that will not return. Ancient Mars can be imagined as a world with a fuller atmospheric reservoir. The air inside that reservoir was never motionless. Some gas was added by volcanoes and activity within the planet. Some was lost to space. When Mars was young, the balance between supply and loss may not yet have been so uneven. But as the interior cooled, the source of new gas weakened. Meanwhile, The sun continued shining, continued sending out its particle wind, and continued acting on the upper atmosphere. The reservoir began losing more than it received. Not suddenly, but persistently. The atmosphere declined, pressure fell, and the range of conditions that allowed liquid water to exist became narrower. What happened to hydrogen is deeply connected to the story of water. If water molecules are broken apart and hydrogen escapes, the planet does not merely lose a light gas, it loses one of the essential components of water. Once hydrogen has escaped into space, it is very difficult for it to return and rebuild water on the surface. The oxygen left behind may become trapped in rocks, form oxidized minerals, contribute to the familiar red color of Mars, or take part in other chemical processes. In this way, loss high above the planet can leave traces far below. The sky loses hydrogen, the ground preserves altered rock, and the planet as a whole gradually becomes drier. Of course, not all Martian water should be imagined as having disappeared through one single pathway. Some may still remain as ice at the poles, beneath the ground, or locked inside minerals. Some may have reacted with rock. Some once existed on the surface and later froze, evaporated, or became buried. But the escape of hydrogen into space shows that an important door was open. Mars did not merely hide its water. Over long periods, it truly lost part of it to space. High in the atmosphere, that story continues today on a much smaller scale. Spacecraft have observed gas escaping from Mars, especially during periods of stronger solar activity. This tells us that atmospheric loss is not only a story from the distant past. It is still happening, although slowly and weakly compared with the planet's long history. Mars now has only a thin atmosphere, but even that thin layer continues interacting with space. It is still illuminated by the sun. It is still touched by the solar wind. It is still leaking away, little by little. The closer we look, the more this process resembles erosion rather than catastrophe. A rocky shoreline does not collapse under the first wave. It wears away gradually, one grain of sand after another, one small crack after another. Mars has changed in much the same way. Its atmosphere has been eroded from above through mechanisms that are tiny but continuous. Light particles escape. Ions are carried away. Molecules are broken apart. Powerful solar events temporarily increase the rate of loss. Then everything returns to the slow, quiet, steady rhythm. What makes this story both sad and strange is that the greatest losses do not always need to be loud. A planet can have its fate changed by processes that are almost invisible. Air leaking into space leaves no clear fracture across the sky. Escaping hydrogen makes no sound. Ions drawn away by the solar wind do not shake the ground. Yet the final result appears everywhere. A thin atmosphere, liquid water struggling to survive, dry riverbeds, vanished lakes, a cold surface, and red dust covering the memories of a wetter world. Mars today is therefore like a world that lost much of itself through doors too small for human eyes to see. The door of weaker gravity. The door through which light hydrogen rises and escapes. The door through which ions are carried away by the solar wind. The door opened by a cooling core that can no longer maintain the strong magnetic shield it once may have had. Each door opens only a little. Each one removes only a tiny amount. But when all of them remain open for long enough, the ancient Martian sky cannot stay the same. And as the atmosphere became thinner, surface water also lost its support. Lower pressure made it harder for liquid water to remain. Heat escaped more easily. Ice became more stable than liquid water. Water vapor could rise higher, be broken apart, and lose hydrogen to space. In this way, the atmosphere and the history of water became inseparable. A leaking atmosphere made water harder to preserve. The loss of water made the planet drier still. The streams that once left their marks in stone gradually became silent, dry channels beneath a sky far thinner than the one Mars had in its youth. Once we reach the upper edge of the Martian atmosphere, where the air becomes so thin that it almost dissolves into the darkness, The story is no longer confined to distant ideas and imagined processes. Humanity has actually sent a spacecraft there, placed it in orbit around the red planet, and guided it through the fragile boundary between atmosphere and space to listen for the faint leakage of a sky that has lost most of its former weight. That spacecraft is called MAVEN, short for Mars Atmosphere and Volatile Evolution. The name may sound long and technical, but its mission goes directly to the heart of the question we have been following. How did Mars lose its atmosphere, and how was that loss connected to the fate of water on the planet? While robots on the surface bend down to read the rocks, soil, and traces of ancient lakes and rivers, this mission looks higher, toward the thinnest reaches of the atmosphere, where the Martian sky comes into direct contact with space. MAVEN entered orbit around Mars in 2014. Since then, after more than 11 years of operation, the small spacecraft has continued its work around the red planet. It did not land on a dusty plain. It does not roll across rocks like Curiosity or Perseverance. Nor does it dig beneath the ground in search of ice. Its work is quieter, passing through the upper atmosphere, measuring gas particles, tracking ions, and observing how the Martian sky responds when the sun reaches it through light, radiation, and streams of charged particles. There is a particular kind of loneliness in that image. Below lies a cold desert, ancient craters, dry valleys, and red terrain stretching toward the curved horizon of the planet. Above is the darkness of space, with almost nothing for the human eye to hold on to. Between those two realms, the orbiter quietly crosses the thinnest boundary of the sky, where an individual gas particle may still be held by Mars, or may already have begun a journey that will carry it away from the planet forever. What matters is that this mission has turned a nearly invisible story into something that can be measured. Even before direct observations like these, scientists knew that Mars had once been different because of the evidence preserved on the ground. Ancient river channels show that water once flowed. Former lakebeds show that water once collected. Minerals formed in water reveal that rock and liquid once interacted under more favorable conditions. But those clues mainly describe consequences preserved on the surface. The actual escape of the atmosphere occurs much higher, in a region far thinner and much more difficult to observe. In the upper atmosphere, everything becomes fragile. The air is no longer as dense as it is near the ground. Gas molecules are farther apart and more easily affected by high-energy sunlight. Some particles are broken apart. Some become ions. Some gain enough energy to travel farther away from the planet. When the solar wind passes by, charged particles high in the atmosphere may be drawn into the interaction and carried away from the remaining air. These processes cannot be seen with the naked eye the way a flowing river can, but instruments aboard an orbiting spacecraft can record their signatures. From the data MAVEN has collected, scientists have gained a clearer understanding that the Martian atmosphere does not escape through only one pathway. Some gas is lost when light particles move fast enough to escape. Some is transformed by solar radiation. Some ions are affected by the solar wind and carried away from the planet. During periods of stronger solar activity, the rate of atmospheric loss can temporarily increase. Each of these processes appears small when viewed over a day, a month, or even a year. But when placed within the billions of years of Martian history, they become major parts of the story of a sky growing thinner. The mission has also shown that Mars did not only lose atmosphere in the distant past. It is still losing a portion of its air to space today, although very slowly. This brings the story closer to the present. It is no longer only an ancient event that ended long ago. Even now, at the upper edge of that pale red atmosphere, gas particles are still leaving. The interaction with the solar wind continues. A fragile region still exists where the planet and space meet. Present-day Mars may represent the final stage of a very long process, but that process has not completely stopped. The small spacecraft can be imagined as a watchkeeper at the edge of the sky, It cannot hold the atmosphere in place for Mars. It cannot repair the layer of air that has become so thin. It can only pass through, measure, record, and send its data back to Earth. Yet this persistent observation makes the Martian sky less silent. What once existed mainly as a hypothesis now has additional evidence. Models of atmospheric escape can now be compared with real measurements. Questions about the solar wind, ions, hydrogen, and the upper atmosphere are no longer suspended only in imagination. They are connected to a specific mission still working around the red planet. More than 11 years of operation also means that MAVEN has observed Mars through many seasons and many different states of the Sun. At times, the Sun is quieter and the particle flow is steadier. At other times, it becomes more active and releases greater amounts of energy into space. When those disturbances reach Mars, the upper atmosphere responds, and instruments in orbit can record the change. A single measurement is only a thin slice of time, but years of continuous observations create a pattern, helping scientists understand that the Martian sky is not as motionless as it appears. This is important because atmospheric loss is a process that requires a long period of observation to understand. Viewed in a single moment, everything seems too small to matter. A tiny amount of escaping gas cannot transform an entire planet immediately. But as measurements continue, and as data are compared under many different conditions of solar activity, those small changes begin to gain meaning. They help scientists estimate how the atmosphere may have been eroded in the past, especially when the Sun was younger and may have been far more active. Mars then appears as a planet caught between two stories. One comes from within. Its small size, weaker gravity, rapidly cooling core, fading global magnetic field, and gradually quieting volcanoes. The other comes from outside, the Sun continuously sending high-energy light and particle winds through space. Where those two stories meet, the upper atmosphere becomes the region most directly affected, and it is within that meeting place that MAVEN has made its measurements. Because of this, the history of Mars is no longer read only from rocks. It is also read from the air that is still escaping. A dry river channel tells us that water once flowed. A layer of sediment tells us that a lake once existed. Magnetized rock tells us that the planet once possessed stronger protection. Measurements in the upper atmosphere reveal how the sky was, and still is, being lost. Each form of evidence comes from a different layer of the planet, but when they are assembled together, they point in the same direction. Mars once had conditions more favorable to water and gradually lost them. Perhaps what makes this mission remarkable is not only its technology. It is also the feeling that humanity is trying to hear something extremely faint from a place incredibly far away. Across tens of millions of kilometers, a human-made spacecraft continues orbiting another planet, measuring individual gas particles, streams of ions, and the response of the sky to the Sun. It tells no story in words, but its data help us understand how a planet changed. Within the silence of space, those numbers become a form of memory. Viewed through that data, the thin Martian sky is not a random condition. It is the result of a long history. The atmosphere may once have been thicker. Water may once have had the opportunity to remain on the surface. A magnetic field may once have protected the planet more effectively. Then the interior gradually cooled, the shield weakened. The solar wind began interacting more directly with the atmosphere, and the air leaked slowly into space. These events did not occur separately. They became intertwined, carrying Mars from a world that may once have been wetter to the cold, dry planet we see today. The mission orbiting Mars is therefore more than one chapter in the history of space exploration. It is a bridge between ancient evidence on the ground and processes that are still continuing high above it. It helps us understand that an atmosphere is not an unmoving curtain. It can be created, replenished, eroded, pulled away, and gradually thinned over time. On Mars, that curtain has become so thin that liquid water can barely find a place to remain on the surface. If the atmosphere became thinner, if the pressure fell, and if warmth became harder to retain, then where did the ancient water of Mars go? Some of it may have been lost to space as hydrogen escaped the planet. Some may still remain locked in polar ice or beneath the ground. Some is preserved within minerals, rocks, and surviving layers of sediment. After looking upward toward the sky, we must turn our attention back toward the ground, searching for places where water no longer flows, but where its traces remain long after the atmosphere became light. At the thin upper edge of the Martian atmosphere, where the last gas particles still held by the planet nearly fade into space, events do not always unfold at a steady pace. There are periods when the sun is quieter, and its stream of particles flows outward like a constant background breeze, gently touching the upper atmosphere. But there are also times when the star becomes far more violent, as though an invisible wave is launched from its brilliant surface, traveling through space, crossing the orbits of the planets, and eventually reaching Mars. This is not a storm in the familiar earthly sense. No dark clouds gather overhead. No rain falls against a roof. No thunder shakes the windows. In space, the storm travels as high-energy radiation, charged particles, and streams of extremely hot, fast-moving material released from the sun. It is silent to human ears and invisible to the naked eye, but it is far from gentle when it reaches a planet with a thin atmosphere and no strong global magnetic field to protect it, as Mars has today. The sun is not a perfectly stable ball of fire. It has rhythms of its own, active regions, sudden bursts of light, and episodes when enormous amounts of material are expelled into space. Sometimes these disturbances alter the surrounding space environment only slightly. At other times, they release far more particles and energy than usual. On Earth, events like these can brighten the auroras, affect satellites, interfere with radio communication, or force technological systems to be monitored more carefully. But Earth still possesses a powerful global magnetic shield, so most of our thick atmosphere is not left directly exposed. Mars exists under very different conditions. Its global magnetic field faded long ago. The magnetized regions that remain within the crust are only scattered patches of protection, not a shield covering the entire planet. The present atmosphere is also extremely thin, especially at high altitudes, where gas molecules become increasingly sparse and vulnerable. So when a powerful disturbance from the sun arrives, the upper atmosphere can be stirred much more strongly. Some gas particles gain additional energy, some molecules are broken apart, some ions are carried away more easily. During these periods, the rate of atmospheric loss can increase. Imagine a very calm lake on a windless afternoon. Only the smallest ripples move across its surface, almost too faint to notice. Then a strong gust passes over it. The water immediately trembles, small waves reach the shore, and leaves floating on the surface are pushed farther away. When the wind stops, the lake grows calm again. But if gusts like these return season after season, the shoreline will not remain exactly as it was. The upper atmosphere of Mars can be imagined as a very thin lake at the edge of space. Under ordinary conditions, it is already leaking. When the sun becomes more active, that leakage may temporarily accelerate. It is important not to think of solar storms as a single blow that stripped away the Martian atmosphere within a few days. Mars did not lose its sky in that way. A planet is not left completely bare because one storm passes and disappears. The real story is slower, longer, and far more subtle. Powerful episodes of solar activity are more like strong winds, occasionally passing over a house whose roof has already weakened. Each one may remove a little more. Not enough to destroy everything at once, but enough to contribute to the damage when the process continues for billions of years. During the early history of the solar system, the younger sun may have been more active than it is today. This would have made the space environment around the planets far harsher. A world with a strong magnetic field and powerful gravity could still reduce some of those effects. But Mars was smaller than Earth, cooled more quickly, had weaker gravity, and eventually lost its global magnetic shield. Under those conditions, bursts of high-energy particles from the Sun may have played a significant role in thinning its atmosphere. Ancient Mars can be imagined as someone walking through a cold, windy region while wearing a coat that grows thinner over time. At first, the coat may have been heavier, with an invisible windbreak outside it. But as the shield weakened and the coat became thinner, every powerful gust was felt more clearly. One gust would not cause the person to collapse immediately, but after countless seasons, the cold would accumulate. For the red planet, the coat is the atmosphere, the windbreak is the magnetic field, and the cold wind is the stream of particles from the Sun. The comparison is not perfect, but it helps us understand how a repeated influence can eventually produce an enormous result. Solar storms pass over Mars without making a sound. Below, the red plains remain still. Ancient craters do not tremble. Sleeping volcanoes do not awaken. Dust is not suddenly torn from the ground simply because a burst of particles from space reaches the upper atmosphere. But higher above the surface, where the air has already become thin, the change can be much more noticeable. Charged particles from the Sun interact with the atmosphere. Energy is transferred into these extremely sparse regions. Some ions escape. A tiny portion of the sky is pulled farther away from the planet. Because this process happens so high above the surface and within air so thin, it requires orbiting missions to observe it. From the ground, a robot can examine rocks, analyze minerals, photograph layers of sediment, and search for traces of ancient water. But to understand how the sky is disturbed when the Sun becomes more active, observations must be made near the outer edge of the atmosphere. Measurements from orbit have helped scientists see that when the solar environment changes, the upper atmosphere of Mars responds as well. That data has made the story more secure. Atmospheric loss is not merely an idea inferred from the distant past, but a process that can be monitored in the present. At times, the Sun releases a large cloud of material into space. It does not resemble a white cloud drifting across the sky, but it is still a cloud in a broader sense, a cloud of charged particles and magnetic fields spreading outward at tremendous speed. When it encounters a planet with a strong magnetic field, much of the flow is bent around the protected region. When it reaches Mars, where the global shield is no longer strong, the interaction with the upper atmosphere becomes more direct. This is when the thin Martian sky is disturbed by a kind of weather that belongs not to the ground, but to space. Space weather is a useful way to describe this part of the story. On Earth, weather means rain, wind, clouds, sunlight, storms, and changes in the air around us. In space, weather comes from the activity of the Sun, particle streams, radiation, solar flares, eruptions of material, and changes in the electromagnetic environment surrounding the planets. Mars has weather on its surface, with dusty winds and enormous dust storms. But it also experiences another kind of weather high above, where the Sun touches the atmosphere in a quieter way. This reveals the Sun as more than a source of light in the story of Mars. It is part of the environment in which the planet must live. Its light can warm the surface. Its energy can help melt ice during favorable periods. But at the same time, strong solar activity can make the upper atmosphere more unstable. A star can both sustain and challenge the worlds around it. On Earth, that challenge is reduced by a magnetic field and a thick atmosphere. On Mars, weaker protection has caused the story to lean more heavily toward loss. Solar storms are not all the same. Some are powerful, while others are weaker. Some reach Mars in an orientation that allows them to produce a stronger effect, while others only slightly alter the environment around the planet. Over the course of history, however, repetition is what matters. A stone is not worn down by a single drop of water, but millions of drops falling steadily over time can reshape it. An atmosphere behaves in much the same way. One powerful solar event cannot explain the entire fate of Mars, but countless events, acting on a system that was already vulnerable, could help thin the sky. The patience of time is what makes planetary stories so different from human life. For us, a storm lasting several days is a major event. For a planet, a few days are almost nothing. What matters is not only the strength of one event, but the combined effect of countless events. Mars has existed for more than 4 billion years. During that time, the Sun has passed through countless cycles, periods of greater and lesser activity, and repeated eruptions of particles and energy. The red planet has remained within that flow, without a strong global magnetic shield like Earth's for much of its later history. Seen this way, the connections between earlier parts of the story become clearer. If Mars were larger, its gravity would be stronger, and it would hold its gases more tightly. If its interior had retained heat for longer, its magnetic field might have survived for a greater span of time. If that magnetic field had remained strong, the upper atmosphere would have been better protected from bursts of solar activity. But as each of those conditions weakened, space storms became part of the erosion process. They were not the only force removing the atmosphere, but they arrived at a time when the planet had already lost much of its ability to defend itself. The more closely we look, the more Mars resembles a world that endured many layers of loss. It did not lose water only because it became colder. It did not lose atmosphere only because its gravity was weak. It did not lose its magnetic field only because the core gradually cooled. It also lived beneath a changing sun, sometimes quiet, sometimes violent, sometimes calm, and sometimes releasing far stronger bursts of particles. All of these factors became intertwined, creating a very long history in which a sky that was once thicker was gradually drawn thinner by causes both inside and outside the planet. Perhaps the strangest image is that of a storm with none of the familiar features of a storm. It does not darken the Martian sky with clouds. It does not pour rain into dry river valleys. It does not send thunder echoing through Valles Marineris. It travels in silence, carried by particles and energy from a star hundreds of millions of kilometers away. When it arrives, it touches the thinnest part of the atmosphere, disturbs particles at the upper edge, and leaves behind a loss too small to notice immediately, but not too small for time. After each event, Mars continues orbiting the Sun. The surface remains red. Dust settles back onto the rocks. Ice remains at the poles and beneath the ground. Ancient river channels preserve the shapes left by water that once passed through them. But high above, a tiny portion of the sky may have left. Across billions of years, those tiny losses accumulate into a profound change. The atmosphere becomes lighter. Pressure falls. Liquid water finds it increasingly difficult to remain. Conditions that once allowed shallow lakes and flowing water gradually close. From these quiet interactions between the sun and the atmosphere, the story returns to the evidence that has been beneath the surface from the beginning. Where did the water of Mars go? As the atmosphere became thinner, pressure decreased, warmth became harder to retain, and liquid water lost the environment it needed to survive for long periods. Some water vapor may have risen into the upper atmosphere, been broken apart by sunlight, and allowed lightweight hydrogen to escape into space. Other water did not leave the planet, but froze at the poles, became hidden beneath the cold ground, or remained trapped within minerals and rocks. The water of Mars, therefore, did not disappear through one single pathway. It did not simply evaporate completely and leave the planet, nor did it remain entirely stored in one hidden place. Its fate divided along many paths. Some was lost to the sky. Some moved beneath the ground. Some froze into ice. Some remained quietly locked within the structures of rocks. By following each of these paths, we begin to see something more clearly. Mars is not simply a planet that lost its water, but a world that both preserved and lost water in many different ways across billions of years. From the story of the thinning atmosphere, we return to the largest question of all. Where did the water on Mars go? Dry river channels, ancient lake beds, and layers of sediment show that water once existed on the planet's surface. Yet Mars today is a cold, dry world covered in red dust. There are no flowing rivers or lakes. There are no seas. There is no familiar rainfall like the kind we experience on Earth. So when we look at the red planet, we must ask not only whether water once existed there, but also where that water went after billions of years of change. Some of the water may have been lost to space. When water vapor rises into the upper atmosphere, sunlight can break water molecules apart into hydrogen and oxygen. Hydrogen is an extremely light element, so it can escape the gravity of Mars more easily. A single hydrogen atom leaving the planet creates no visible event. No stream of water rises into the sky like smoke. But over millions and billions of years, that small and continuous loss may have removed a significant portion of the planet's ancient water. Even so, not all the water on Mars escaped into space. This is important to understand. Mars is not like a container that was completely emptied. Some water left the planet, but another portion may still remain, no longer resting on the surface as rivers, lakes, or seas. It may exist within the polar ice, in ice buried beneath the ground, inside rocks, or within minerals that formed through interaction with water. The easiest form to imagine is ice. Water ice still exists at both Martian poles. The bright white polar regions are not made only of dust or rock. They also contain water preserved in solid form. In addition to water ice, Mars has carbon dioxide ice that changes with the seasons. When temperatures fall, carbon dioxide can freeze into a layer over the surface. When conditions become warmer, it sublimates directly back into gas. But the water ice at the poles is important evidence that Mars has not lost all of its water. Ice may also exist beneath the surface. Liquid water has difficulty remaining stable on Mars because the pressure is low, the atmosphere is thin, and temperatures are cold. But water buried underground can be better protected. The overlying layer of dust and rock blocks some direct sunlight and helps the ice remain stable over long periods. Beneath the cold Martian soil, there may still be regions of stored ice. They do not appear as lakes, but they remain part of the planet's surviving water. Another portion of the water may have entered the rocks. When water remains in contact with rock for long enough, it can alter that rock and create hydrated minerals. This does not mean that liquid water is trapped inside the stone like a hidden pocket. It means that water participated in the formation or transformation of the mineral. Long after the water stopped flowing, the mineral can continue preserving evidence that water was once present. This is an extremely important form of evidence. An ancient stream may have disappeared long ago, yet it can still leave traces within the rocks. Water may once have seeped through fractures, soaked mud and sand, reacted with minerals, and produced new materials. Then the surface dried, dust settled over it, and time continued passing. But the signature of water remained inside the structure of the rock. When orbiters or robotic explorers discover clay, mineral salts, or hydrated minerals, they are reading part of Mars's water history. An ancient lakebed helps make this easier to picture. When water once collected inside a basin, it carried mud, sand, and minerals down from higher ground. These materials settled onto the bottom, building one layer of sediment after another. If the water remained long enough, it also interacted with the surrounding rock and altered the minerals. Later, the lake dried and the surface became barren, but the sedimentary layers remained. Much later, when a rover passes through and analyzes the rocks, it can recognize that this place was once an environment shaped by water. A dry river channel on Mars, therefore, tells us more than the fact that water disappeared. It shows that water once flowed long enough to reshape the surface. A dried lakebed is not only a sign of aridity. It may also preserve layers of material that once settled through water. A rock containing hydrated minerals is no longer wet, but it still carries evidence that water once passed through it. The water of Mars has therefore followed many different paths. Some escaped into space as hydrogen left the upper atmosphere. Some froze at the poles. Some may remain beneath the cold ground. Some became locked within minerals. and some survives only through ancient landforms such as river channels, valleys, lakebeds, and sedimentary layers. There is no single place containing the entire answer. To understand where the water went, we must examine the atmosphere, the ice, the soil, and the rocks together. This perspective creates a more balanced story. Mars is not a planet that has lost every trace of water, but it is also no longer a world where water is easily visible, as it is on Earth. Its water has been dispersed, transformed, and hidden. Some left the planet. Some remains within ice. Some lies deep beneath the surface. Some became a chemical trace inside minerals. This distribution makes the study of Martian water more difficult, but also more meaningful. When scientists study water on Mars, they are not only asking where it remains today. They also want to know how long it once existed, what kinds of environments held it, and whether it ever created conditions favorable for life. Liquid water is essential to life as we know it, but water alone is not enough. Life also requires time, energy, and a suitable chemical environment. Every trace of water on Mars is therefore a clue to the planet's past. We should also be careful not to imagine that ancient Mars was simply another Earth. It may once have been wetter than it is today, but that does not necessarily mean it possessed vast oceans and a stable climate for a long time. Water may have appeared only during certain periods or in certain regions, then disappeared as the atmosphere thinned and the climate became colder. Some places may have held shallow lakes. Others may have experienced temporary flows. In some regions, water may only have seeped into rock and left behind chemical traces. Looking across the entire story, we can see that Martian water did not meet a simple end. It did not all escape into the sky. Nor did it remain intact as rivers and lakes. It moved into many different forms. Gas lost to space, polar ice, underground ice, hydrated minerals, and geological traces. The river may have vanished from the surface, but its history remains preserved in many different places. So when we look at a dry valley or an ancient lakebed on Mars, we are not seeing only the absence of water. We are seeing evidence of a planet that was once different. Water may no longer flow before our eyes, but it continues to leave traces in the rocks, the ice, the soil, and the atmosphere that has grown so thin. Those clues reveal that Mars is not simply a cold red desert, but a world that once held water, changed over time, and still preserves many silent traces of a wetter past. Once we understand that the water on Mars did not disappear in only one way, we can look more closely at the place that preserves the greatest number of clues: the rocks. Water may no longer flow across the surface as it once did, but when it passed through the soil, collected in ancient lakes, seeped into fractures, or came into contact with stone, it left behind subtle changes. Those changes remain in the colors of the rocks, in layers of sediment stacked one above another, in distinctive minerals, and in the shapes of ancient landscapes. When water flows across a surface, it does not simply pass by and vanish. It can carry sand, mud, and extremely fine particles with it. As the water slows, those particles settle. Over time, they build one layer after another. If water remains long enough, it can also transform the rock itself. The original rock comes into contact with water and gradually changes into a different kind of material. So even when no water is visible today, the rocks can still reveal that a place was once wetter than it is now. Imagine a cliff inside an ancient crater on Mars. From a distance, it may look like nothing more than a reddish-brown wall of stone. But viewed up close, the cliff contains many layers resting on top of one another. Some are fine, while others are coarser. Some are bright, and some are dark. Each layer may come from a different period. At one time, water may have flowed in. At another, a lake may have rested quietly. Mud may have dried. Wind may later have covered the surface with more dust. Each layer of rock is like a page in a very old book. Rovers are sent to Mars to read those pages. They do not read with human eyes, but with cameras, wheels, drills, and scientific instruments carried on their bodies. A rover can approach a rock, photograph it in great detail, grind or drill into a small part of its surface, and then examine what lies inside. From this data, scientists can determine whether the rock formed in a dry environment, in the presence of water, or in a setting that changed over time. One important sign is clay. On Earth, clay often forms when rock remains in contact with water for a sufficiently long period. So when scientists discover clay on Mars, they have good reason to believe that water once interacted with the rock there. This does not necessarily mean the location once held a vast sea or a long river, but it does show that water was present and may have remained long enough to alter the material. In addition to clay, there are different kinds of mineral salts. Put simply, these are substances left behind after water once dissolved material and then gradually evaporated or drained away. A shallow body of water may slowly dry up. As the water disappears, substances that were once dissolved within it remain behind and form mineral deposits in the soil and rock. These signs help us understand that certain places on Mars once held water, but later became drier. Another kind of evidence involves carbon dioxide, water, and rock. In simple terms, when gases in the atmosphere, liquid water, and rock react under suitable conditions, they can create certain distinctive minerals. These minerals help scientists investigate what the ancient Martian atmosphere may have been like. If Mars once had more atmospheric gas and liquid water on its surface, part of the evidence for that interaction may still remain within the rocks. The important point is that no single clue tells the entire story. Clay shows that water once altered rock. Mineral salts may indicate that water once receded or evaporated. Other minerals help connect liquid water with the ancient atmosphere. When these clues are considered alongside landforms, such as dry river channels, ancient lakebeds, and regions that once accumulated sediment, the picture of early Mars becomes clearer. An ancient lake basin can reveal this especially well. Water once flowed into a depression, carrying mud, sand, and material down from higher ground. As the water slowed, those particles settled onto the bottom. One layer formed on top of another. If the lake survived long enough, the water and rocks had time to interact. Later, the lake disappeared, the surface dried, and dust settled over it. But the layers of rock remained, preserving evidence that water had once existed there. This is why rovers are so important. Orbiters can observe broad regions from above, including ancient river channels, former lake beds, and areas with unusual colors. But understanding the finer details requires a machine on the ground. A rover can move close to individual layers of rock, examine their surfaces, drill into their interiors, and send the data back to Earth. It is like a geologist working very slowly on a distant planet. When a rover drills into rock, it is searching for material inside that may preserve information more clearly. The exposed surface of a rock has endured wind, dust, and radiation for an extremely long time. It may have been worn down or chemically altered, but the interior can sometimes retain clearer evidence of the ancient environment. Rock powder collected by a drill can reveal what the stone is made of, the conditions in which it formed, and whether it ever came into contact with water. Rock layers also help us understand change over time. If we examine only one isolated stone, we learn only a small part of the story. But when we study many layers resting on top of one another, we can see how the environment changed. A lower layer may show that the region was once wetter. A layer above it may record a later, drier period. This helps us understand that Mars did not lose its water in a single moment. Its environment changed gradually through many stages. Rocks also prevent us from letting our imaginations travel too far. When we hear that Mars once had water, it is easy to picture a planet much like Earth. But the evidence preserved in stone shows that the story must be understood more carefully. In some locations, water may have remained for a considerable time. In others, it may have appeared only briefly. Some places may have contained shallow lakes. Others may have experienced short-lived flows. Some environments may have been milder, while others were saltier, drier, and less capable of preserving liquid water for long. This connects to a much larger question. Was ancient Mars ever favorable for life? Liquid water is important for life as we know it, but water alone is not enough. A relatively stable environment, necessary chemical ingredients, and sufficient time are also required. When rocks show that a place once contained a lake, clay, or layers of settled mud, that location becomes more interesting. Not because we know life existed there, but because it once offered conditions more favorable than the cold, dry surface of Mars today. Rovers are therefore more than machines traveling across Mars. They are humanity's way of asking questions directly of the rocks. Every image, every drilled sample, and every sign of clay or mineral salts helps us understand another part of the story. They show that water was not merely an idea belonging to the distant past. Water once touched the surface, collected in low areas, seeped into stone, and transformed the material around it. And after the water disappeared, those changes remained. There is something remarkable about the way Mars tells its story. The planet no longer shows us rivers flowing across its surface. It no longer allows us to see the waters of its ancient lakes, but it preserves what the water did. Rocks retain layers of sediment. Minerals preserve signs of past contact with water. The landscape keeps the pathways carved by flowing streams. Through these traces, a planet that appears dry and rigid can still reveal part of its wetter past. From here, the search for water on Mars is no longer only a search for where water remains today. It is also a search for what water once left behind. Which lakes did it create? How did it transform the rocks? Which layers of mud did it deposit? And how did those environments eventually dry out? Every answer helps us understand the youth of the red planet more clearly. The deeper we read into the rocks, the more we see that Mars is not an empty world, but a planet whose past remains preserved within every layer of stone resting silently beneath the red dust. When rocks on Mars preserve traces of water, they tell us more than the fact that a place was once wetter. They also lead us back to a larger question. What was the atmosphere like at that time? Water cannot remain on the surface by itself. It needs more suitable temperatures, higher pressure, and a layer of air thick enough to retain some warmth. One gas plays an especially important role in this story: carbon dioxide, commonly written as CO2. Carbon dioxide is a familiar component of the atmospheres of many planets. Today, most of the Martian atmosphere is made of this gas. The problem is that the atmosphere is far too thin. It contains a heat-trapping gas, but there is not enough of it to retain warmth as effectively as a thicker atmosphere could. As a result, present-day Mars remains cold and dry, with low surface pressure, and liquid water can survive only briefly on the surface. This may sound like a contradiction. If the Martian atmosphere is composed mainly of carbon dioxide, and carbon dioxide can trap heat, why is Mars still so cold? The answer lies in the thickness of the atmosphere. Even a blanket made from good insulating material cannot provide much warmth on a cold night if it is extremely thin. The atmosphere of Mars today is like a blanket that has become far too thin. It still surrounds the planet. Mars still has winds and delicate clouds. But the atmosphere is not thick enough to retain much warmth near the surface. In the past, if Mars possessed much more carbon dioxide, the story may have been different. A thicker atmosphere could have created higher surface pressure. With greater pressure, liquid water would have had a better chance of remaining stable. A denser atmosphere might also have retained heat more effectively, allowing some regions or certain periods on Mars to become less cold than they are today. This does not mean that ancient Mars was necessarily warm like Earth, but it may have experienced intervals that were more favorable for water. We can imagine ancient Mars beneath a sky thicker than the one surrounding it today. That sky may not have been blue, humid, or filled with clouds like Earth's. it may still have appeared dusty, cold, and unfamiliar. But with a heavier layer of gas surrounding the planet, the surface below would have been less exposed to the cold of space. During the day, sunlight warmed the ground. At night, some of that heat could have remained for longer. The difference may not have transformed Mars into a comfortable world, but it might have been enough for liquid water to appear during certain periods. Carbon dioxide is also connected to the rocks. When atmospheric gas, water, and rock come together under suitable conditions, they can form certain distinctive minerals. These minerals help scientists learn more about the ancient atmosphere of Mars. If the planet once had more atmospheric gas and liquid water on its surface, some evidence of those interactions may still remain locked within the rocks. The word climate can be understood here as the general condition of an environment over a long period of time. Whether it is hot or cold, dry or wet, whether the atmosphere is thick or thin, and whether water can easily survive. The ancient Martian climate is difficult to reconstruct because we cannot return to the past and measure it directly. Instead, scientists rely on the evidence that remains: rocks, sedimentary layers, ice, minerals, dry river channels, and the atmosphere that surrounds Mars today. Each clue reveals only a small part of the story, and scientists assemble those pieces to understand how the planet changed. One question still under investigation is how thick the ancient atmosphere of Mars truly was. It may have been denser than it is today, but determining how much denser is not simple. If it was still too thin, it would have struggled to retain heat and support liquid water for long periods. If it was sufficiently thick, it might have created intervals of milder conditions. But Mars lies farther from the Sun than Earth and receives less sunlight, so even a larger amount of heat-trapping gas may not have been enough to keep the planet warm continuously. This is one reason the ancient climate of Mars remains an open area of study. Mars may not have been warm all the time. It may instead have passed through shorter periods when conditions became more favorable than usual. Volcanoes could have added gases to the atmosphere. Changes in the planet's axial tilt may have redistributed ice and water vapor. Large impacts could also have warmed the environment temporarily. During those periods, if the atmosphere was thicker than it is today, liquid water may have flowed across the ground, collected in shallow lakes, and left traces in the rocks. It is important not to imagine carbon dioxide as a simple switch that turns climate on or off. A larger amount of heat-trapping gas does not automatically mean that Mars must have been warm, nor would the loss of that gas have made the planet instantly cold. The real story is far more complex. Atmospheric composition is important, but so are atmospheric thickness, distance from the Sun, airborne dust, surface ice, volcanic activity, and the planet's ability to retain gas over time. Together, these factors determine whether liquid water can survive on the surface. As the atmosphere around Mars became thinner, conditions grew increasingly difficult for water. Pressure fell. Heat escaped more quickly. Nights became colder. Ice became more stable than liquid water. If water reached the surface, it could not remain there for long. It might freeze, evaporate, or disappear from its liquid state very quickly. The thinning of the atmosphere was therefore an important step in the transformation of Mars from a planet that may once have been wetter into the cold, dry world we see today. The rock layers discussed earlier help reveal this change more clearly. In some places, rocks preserve signs of water. In others, they record environments that became drier, saltier, or more severe. This suggests that Mars did not transform in a single moment. Its climate may have passed through many stages. At times, water appeared. At other times, lakes dried. Minerals formed as water retreated. The surface then became drier and dustier. Throughout each of these stages, the atmosphere remained a crucial part of the background conditions. Carbon dioxide still surrounds Mars today, but only within a thin atmosphere. It is like the surviving trace of a sky that may once have been heavier. It reminds us that the question is not only which gases a planet possesses, but how much gas is present, how long it can be retained, and how it interacts with water, rock, and ice. A greater quantity of gas in the past may have helped preserve heat more effectively. But if the atmosphere was gradually lost to space or became trapped within rocks, the planet's ability to remain warm would also have weakened. This story connects many different parts together. The small size of Mars gave it weaker gravity. Its cooling core caused the global magnetic field to fade. The solar wind then interacted more strongly with the upper atmosphere. Some atmospheric gas escaped into space. As the atmosphere became thinner, the remaining layer was no longer dense enough to retain heat effectively. Without that warmth, liquid water could not remain on the surface for long. As the water disappeared, rocks and minerals became the places where the last traces of wetter periods were preserved. Carbon dioxide is therefore more than a minor detail in the Martian atmosphere. It is one link in the larger story of the planet. It is connected to temperature, pressure, water, and rock. It helps explain how a thicker ancient atmosphere may have allowed liquid water to appear. It also helps us understand why the thin atmosphere of today can no longer support liquid water on the surface. The final answer, however, still requires caution. Ancient Mars may once have had more heat-trapping gases, a thicker atmosphere, and periods warmer than the present. But the planet was not necessarily warm for long stretches in the way Earth is. Water may have appeared only during certain periods and in certain regions, then retreated when conditions changed. This uncertainty is precisely why the continued study of Martian rocks, ice, and atmosphere remains so important. When we look at Mars today, we see a cold and dry world. But when we examine the rocks more deeply, study the thin atmosphere around the planet, observe the polar ice, and trace the signs of ancient water, a more complex story emerges. The ancient atmosphere may once have helped Mars retain warmth more effectively. Water may have flowed during more favorable intervals. Rocks recorded interactions between water and the ancient air. Then, as the atmosphere thinned, everything gradually changed. The larger picture begins to come into focus. Mars did not lose its water for only one reason. It did not become cold and dry because of a single event. Its present condition is the result of many connected factors: a small planet, an atmosphere gradually lost, a heat-trapping layer that became too thin, water that could no longer remain stable, and rocks that preserved the surviving evidence. The atmosphere, temperature, water, and rocks are not separate stories. They are all parts of the same history. The history of a planet that once experienced conditions different from those of today, and then slowly became the Mars we now see. As the Martian atmosphere became thinner, liquid water could no longer remain easily on the surface. Low pressure, cold temperatures, and dry air made it difficult for rivers and lakes to survive as they had in the past. But that does not mean water completely disappeared from the red planet. Some was lost to space, some became trapped within rocks, and another portion still remains as ice. Mars today has no blue seas or flowing rivers. But at both poles, water is still preserved within layers of frozen material. Seen from a distance, the polar regions appear brighter than the surrounding red terrain. Part of this covering changes with the seasons because carbon dioxide gas freezes into ice and then returns to vapor as temperatures rise. Yet beneath and within the polar regions, water ice remains an important part of present-day Mars. It shows that the planet did not lose all of its water. It simply no longer preserves water in the easily visible forms it once may have had. Water ice is simply water in its solid state. That may sound obvious, but on Mars it is extremely important. On a cold planet, ice can survive much longer than liquid water. Liquid water requires suitable pressure and temperature to remain stable. Ice, however, can rest undisturbed in regions cold enough to preserve it, especially when it is covered by soil or dust. So as the Martian surface became colder and drier, some water stopped flowing and entered a kind of suspended state within the ice. Ice may exist not only at the two poles, but beneath the surface in many other regions. The layer of red soil above it acts like a thin covering. It does not warm the planet, but it can block some direct sunlight and protect the ice from the outside environment. Beneath that dust, in places cold enough, water may remain preserved for extremely long periods. It does not appear as the surface of a lake. It does not reflect the light. It simply rests beneath the ground, like a piece of the past stored in darkness. This image makes Mars seem less like a completely lifeless, dried-out desert. At the surface, everything appears severe: rock, dust, wind, cold plains, and a thin sky. Yet beneath the soil, regions of ice may still quietly survive. Water no longer flows through rivers, but it has not vanished from every part of the planet. It has changed the way it exists. What was once a current on the surface has become ice hidden deeper underground, quieter, and more difficult to detect. Scientists are interested in subsurface ice because it helps reveal the ancient climate of Mars. Climate here can be understood simply as the planet's general condition over long periods, whether it was colder or warmer, drier or wetter, where ice was located, and how water moved. If ice now lies beneath the ground across many regions, it may show that water and water vapor were distributed differently in the past. At times, ice may have spread more widely. At other times, it may have retreated toward colder areas. These changes form part of the climate history of the red planet. Mars also experiences cycles of extremely slow change. Over long periods, the tilt of the planet's axis can vary, changing the way sunlight reaches different regions. When that happens, ice and water vapor can shift from place to place. A region once cold enough to preserve ice may become less stable. Another region may become more favorable for ice to accumulate. These processes happen very slowly, but over hundreds of thousands or millions of years, they may cause water on Mars to migrate across the planet. Ice beneath the red dust is therefore more than frozen water. It is a sign of very long seasons within Martian history. It helps us understand how the planet continued to change after its rivers and lakes disappeared. Water could no longer flow freely, but it may still have moved in other ways, evaporating into the atmosphere, settling again in colder regions, becoming buried beneath the ground, and remaining there as ice. Each layer of ice may contain part of the history of the period in which it formed. To search for ice underground, humans cannot rely only on ordinary vision. Often, the surface shows nothing more than red soil and broken rock, with no obvious sign of what lies below. Spacecraft orbiting Mars must use special measurements to look beneath the ground. Some instruments send signals through the surface and receive the returning echoes, helping scientists identify places that may contain ice. Others measure the composition of the near-surface material and look for signs of hydrogen, an important component of water. From this data, scientists create maps of regions likely to preserve ice. Rovers on the surface also contribute to this story, even though they cannot dig deeply across the entire planet. They observe rocks, soil, sedimentary layers, and the surrounding environment. Their discoveries help connect the ice that remains today with water from the past. An ancient lake basin, a rock layer once altered by water, or a region containing minerals formed through water all show that the planet once possessed a more complex water cycle than it does now. Subsurface ice is one surviving part of that cycle. This is also important for future missions. If humans eventually send more equipment, or even people, to Mars, water will be an extremely valuable resource. Ice could provide drinking water, help produce oxygen, and support many other needs. But before it can be considered for use, scientists must understand where the ice is located, how deeply it is buried, whether it is relatively pure or mixed with other materials, and whether it can be reached. Studying ice, therefore, helps us understand not only the past, but also the future of Martian exploration. Still, caution is necessary. The presence of ice does not mean that Mars today offers an easy environment for life. Ice trapped in frozen soil is not the same as a lake of liquid water. It is locked in a solid state under extremely harsh conditions. The surface remains cold and dry and is exposed to far more radiation than Earth. Martian ice is evidence that water still exists, but it does not make the planet Earth-like. It simply shows that water has found another, quieter place to remain. The difference between liquid water and ice is also an important part of the story. Liquid water can flow, dissolve substances, carry material, create sedimentary layers, and alter rocks more quickly. Ice is more still. It preserves water, but it does not create the same kind of environment as a river or lake. So when Mars changed from a world that may once have supported liquid water into a colder one, its water did not simply become less abundant. Its role also changed. From a force capable of reshaping the surface, it became material stored in the soil and at the poles. Beneath the red dust, these regions of ice are like water that has fallen silent. They do not tell their story through the sound of flowing currents, but through their location, depth, and distribution. If ice lies near the surface in a particular region, that reveals the cold and dry conditions that allowed it to survive. If it lies deeper, it may have been buried over time. If ice appears at many different latitudes, it may show that the Martian climate once changed enough to move water before it settled into its present form. Seen this way, Mars still preserves water, but not in the familiar image we usually associate with it. Water no longer flows through valleys. It no longer collects in large lakes on the surface. It no longer forms open streams beneath the sky. Instead, it remains within the polar ice, the frozen ground, minerals, and layers of rock that once came into contact with water. The red planet did not lose its water completely. It moved that water into places that are more difficult to see. This makes the story feel gentler after so much discussion of loss. The atmosphere grew thinner. The solar wind helped draw gas into space. Hydrogen escaped. Liquid water could no longer remain easily on the surface. Yet underground, some of the water still sleeps. It can no longer tell the story of the past through flowing rivers, but it remains evidence that Mars once possessed water and still preserves part of it today. When we look across the cold red plains, we can imagine regions of ice resting beneath the thin covering of dust, unchanged through immense stretches of time. High above, the thin atmosphere moves with the wind. Across the surface, rocks and sand lie beneath the pale sunlight. And below, water survives in another form, motionless, without a sparkle, but still real. It is a quieter and deeper Mars, where the past remains not only within the rocks, but also within the ice. The search for water on Mars does not lead only toward dry river channels or ancient lakebeds. It also leads beneath the surface, toward places where water may have been preserved after the climate changed. Ice beneath the red dust reminds us that losing water does not always mean that it disappears completely. Sometimes water simply leaves our sight, changes into another state, and rests within the planet's cold darkness, waiting for humanity to continue the search. Present-day Mars can easily feel like a world that has come to a stop. Red ground stretches beneath a thin sky, ancient craters lie motionless, and valleys that once held water remain only as dry lines carved into stone. There is no rain to soften the soil, and no rivers or lakes reshaping the surface as they do on Earth. But this silence does not mean the red planet is completely still. Observed over a long enough span of time, Mars is still changing, only at a very slow pace. On Mars, change often arrives gently. It does not come with the sound of water, with forests moving in the wind, or with thick clouds and heavy rain. It comes through dust. Martian dust is extremely fine. It covers rocks, clings to the ground, settles in low areas, spreads across broad plains, and can be lifted from the surface by the wind. The planet's atmosphere is much thinner than Earth's, but it is still thick enough to produce moving air. When wind passes over dry regions, it carries small particles of dust upward and releases them somewhere else. So even though the surface appears ancient, rigid, and dry, it is still being altered little by little. A thin layer of dust can change the color of the ground. A dark region of rock may be covered and become lighter. Somewhere else, the wind may sweep the dust away and expose the surface beneath it. These changes are not dramatic over a single day, but they accumulate with time. Mars does not need flowing water in order to change. In its cold and dry present, wind and dust have become the main forces that keep the surface in motion. At times, dust remains only lightly suspended in the air. The sky becomes slightly hazier, the sunlight a little weaker, and the horizon softer and paler. But there are also times when far more dust is lifted and spreads outward, creating enormous dust storms. Dust storms on Mars carry no rain, unlike storms on Earth. They are dry storms formed by wind and countless tiny particles. They may begin within one region and then expand across the plains, pass over craters, and obscure immense areas. Some Martian dust storms can spread across great distances and continue for long periods. Sometimes they affect only one region. At other times, they grow so large that nearly the entire planet becomes covered by a dim veil of dust. When that happens, the amount of sunlight reaching the surface decreases significantly. This matters greatly for solar-powered equipment because dust in the atmosphere and dust settling on exposed surfaces can reduce the light available to it. For scientists, these storms demonstrate that even the thin Martian atmosphere is capable of transporting dust on a planetary scale. What is unusual is that these dust storms do not make Mars feel alive in the familiar earthly sense. They do not bring water back. They do not restore rivers or lakes. They do not soften the ground. But they remind us that the red planet still has weather. A cold, dry form of weather with fewer components than Earth's, yet still shaped by the movement of air, light, and material across the surface. In addition to dust, Mars changes with the seasons. The reason lies in the tilt of the planet's rotational axis. Mars is slightly tilted as it travels around the Sun, much as Earth is. Because of this tilt, one hemisphere receives more sunlight during one part of the year while the other receives less. As the planet continues along its orbit, the situation reverses. These changing patterns of sunlight create the seasons. Seasons on Mars last longer than seasons on Earth because a Martian year is also longer. The red planet takes nearly twice as long as Earth to complete one orbit around the Sun. Seasonal changes therefore unfold more slowly. The direction of sunlight shifts gradually. A polar region enters an extended period of cold and later receives more light as the season changes. On a planet where most water now exists as ice, these changes in sunlight are very important. At both poles, the ice responds visibly to the seasons. When winter arrives and temperatures fall, some carbon dioxide in the atmosphere freezes into a layer covering the surface. When the warmer season returns, this ice does not melt into liquid. It changes directly from a solid back into a gas. This process is called sublimation, which simply means that ice becomes gas without first passing through a liquid state. The Martian polar regions, therefore, do not keep the same appearance throughout the year. They expand, contract, brighten, and darken with the seasons. Beneath these seasonal layers, water ice remains the more important part of the longer Martian story. Water ice does not appear and disappear as quickly as seasonal carbon dioxide ice. It can remain preserved for much longer, especially in extremely cold regions. This connects the earlier story with the planet's present condition. Water no longer flows across the surface, but it may still remain as ice at the poles or beneath the soil. The seasons do not turn that water into rivers, but they show that water and ice are still part of Mars today. Dust, ice, and sunlight interact in subtle ways. A layer of dust covering ice can darken the surface, allowing it to absorb more sunlight. A brighter region may reflect more light and remain colder. As wind moves the dust, it can change the way the surface absorbs heat. When the temperature changes, the ice responds as well. These processes do not transform Mars into a warm world. but they show that the planet still follows rhythms of its own, even though those rhythms are much slower and drier than those of Earth. In some regions, the wind also creates small patterns in the sand. Ripples, dust streaks, and dunes can change over time. A single image may make everything appear motionless. But when images taken far apart in time are compared, the sand can be seen to have shifted, the dust to have moved, and the surface to have been rearranged. Mars does not need rain in order to change. Wind and dust alone are enough to leave marks behind. This helps us view the red planet with greater balance. Earlier parts of the story focused heavily on loss. An atmosphere that may once have been thicker gradually became thinner. The global magnetic field weakened. Liquid water could no longer remain stable, and some atmospheric gas and hydrogen escaped into space. But present-day Mars is not merely the remainder of everything it has lost. Its story is still unfolding. With every season, the polar regions change. With every wind, dust may move. Each day, sunlight warms the ground slightly, and then that warmth quickly escapes when night arrives. A day on Mars may begin in intense cold. As the sun rises, pale light spreads across the red ground, warming the rocks and sand a little. The thin air above the surface begins to move. Fine dust may rise close to the ground. By afternoon, the sunlight begins to slant, and the shadows of rocks grow longer. When night arrives, warmth escapes rapidly because the atmosphere is so thin. This rhythm repeats through long, cold, dry days. It is extremely quiet, but not completely empty. Rovers on Mars have recorded this rhythm of change. They have seen dust settle on their equipment, watched the sky grow dimmer during dusty periods, and observed sunlight changing through the day and across the seasons. These machines do more than help humanity read the past within the rocks. They also reveal present-day Mars as an environment that is still changing, even if those changes are less dramatic than they are on Earth. On a cold, dry planet, a layer of dust on a machine, a hazier sky, or a shift in the light can all provide important data. It could be said that present-day Mars moves through the forces that remained after liquid water withdrew from its surface. In place of rivers, there are winds carrying dust. In place of rain, there is ice expanding and contracting with the seasons. In place of seas, there are frozen polar regions preserving water in solid form. In place of a humid climate, there is a sparse and dry system that still follows recognizable patterns. These patterns help us understand that a planet does not need to resemble Earth in order to have weather. Mars today is a slow world. Its surface does not change quickly. Its main processes are not loud. Many changes become visible only after days, seasons, or years of observation. Yet this slow pace suits the history of the planet. After billions of years of losing atmosphere and liquid water, what remains has not stopped moving. It has simply entered a smaller rhythm, dust rising, ice changing with the seasons, and sunlight slowly shifting across the rocks. Seen this way, Mars no longer appears only as a planet of the past. Its dry river channels and ancient lakebeds remain deeply important, but they are not the entire story. Present-day Mars is also leaving traces of its own. Today's dust may settle over ancient rocks. Today's wind may rearrange the sand. Today's ice may expand and retreat across the polar regions. These small changes will continue to be recorded on the surface, like delicate lines connecting the past with the present. After following the water that was lost, the ice that remains, and the rock layers that preserve evidence of water, we can pause for a moment in the present-day world of Mars. It is a cold and dry planet, but not one that has stopped moving. Dust still travels through the thin air. Ice still responds to the seasons. Sunlight still changes direction as the tilted planet follows its orbit around the sun. These motions do not return Mars to its wetter past, but they show that the red planet still possesses a very slow rhythm of its own. In the end, Mars emerges as more than a planet that once held water, or a world that lost most of its thicker, warmer atmosphere. It is still changing, but in a deeply quiet way. Across its surface, dust continues to move over the wide plains. Ice still appears and retreats with the seasons. Thin winds remain strong enough to cover old footprints, soften the marks of rover wheels, and write new lines across the red soil. Mars no longer possesses the lively rivers, lakes, rain, and storms familiar to Earth, but neither is it a completely motionless world. Within the cold, the dryness, and that fragile atmosphere, the red planet still carries a very slow breath of its own. And it is these subtle movements that make us feel its story has not truly ended. When we look at Mars today, we see a planet that still has seasons, drifting dust, and changing ice at the poles. But none of those things are enough to return it to a wetter age. Liquid water can no longer remain on the surface for long. The atmosphere is too thin to retain heat effectively. Evidence preserved in the rocks shows that the past was once different, but present-day Mars reminds us that a planet that once had water may not be able to preserve favorable conditions over long periods of time. From here, the story is no longer only about Mars. It opens into a much larger question. What makes a world capable of supporting life? When people talk about a planet that may be able to support life, they often begin with the distance between that planet and its star. If it is too close, the planet may become too hot. If it is too far away, it may become too cold. Between those extremes lies a more moderate region where liquid water may be able to exist on the surface, provided that other conditions are also suitable. This region is often called the habitable zone. Put simply, it is the range around a star that is neither too hot nor too cold. But Mars shows that distance is only one part of the story. The red planet is not so far away that every possibility for water was ruled out from the beginning. Its surface preserves evidence of ancient lakes, flowing water, sedimentary layers, and minerals connected to water. This shows that there were periods when its environment was more favorable than it is today. But then the atmosphere became thinner. The global magnetic field weakened. Liquid water lost the conditions it needed to remain, and the planet gradually became cold and dry. A world may pass through wetter periods and still fail to preserve the stability those conditions require. A habitable planet, therefore, needs more than the right distance from its star. It also needs an atmosphere that can endure. The atmosphere is like a covering wrapped around the planet. It creates pressure, helps retain warmth, gives liquid water a chance to remain stable, and protects the surface from some of the effects of space. If that atmosphere is too thin, heat escapes quickly, pressure remains low, and water struggles to survive. If the atmosphere is gradually lost and cannot be replenished, a planet may shift from a once more favorable condition into a much harsher environment. Earth has preserved an atmosphere that is far thicker and more stable than the atmosphere of Mars. One reason is that Earth is larger and has stronger gravity, allowing it to hold on to gases more effectively. Another is that Earth's interior remains active, supporting many long-lasting geological processes. Just as importantly, Earth possesses a global magnetic field, an invisible layer of protection that deflects many charged particles coming from the Sun. These factors do not act separately. Together, they create a more stable environment for water and for life as we know it. Mars is smaller, which placed it at a disadvantage from the beginning. Its weaker gravity made it more difficult to preserve a thick atmosphere over long periods. Its interior cooled more quickly, and deep planetary activity weakened earlier. As the global magnetic field faded, the upper atmosphere became more directly exposed to the Sun. Over billions of years, portions of that atmosphere escaped into space. As the atmospheric layer thinned, liquid water also lost the support it needed to remain stable. This shows that a planet does not only need to begin with favorable conditions, it must also be able to preserve them for long enough. Time is an extremely important factor. A lake that appears for a few years is not the same as one that survives for thousands or millions of years. A brief flow of water following a temporary warming event is not the same as a stable system of rivers and lakes. For life as we know it, an environment needs a certain degree of persistence. It does not have to be perfect, but it must remain stable enough for chemical processes to have time to unfold. Mars may once have experienced favorable periods, but the question is how long those periods lasted and how stable they truly were. Water is not the only requirement either. It is extremely important because life on Earth depends on liquid water. Water allows substances to dissolve, move, and react with one another. But a planet with water does not necessarily have life. It also needs suitable chemical ingredients. It needs a source of energy. It needs an environment that does not become too extreme too quickly. If water appears and disappears too rapidly, or if conditions change too violently, the formation and survival of life become much more difficult. A planet can be imagined as a house. Placing that house where it receives the right amount of light is important, but it is not enough. It needs a roof to protect it from cold winds. It needs a strong foundation that will not collapse over time. It needs water, warmth, and the ability to withstand changes from outside. If the light is moderate, but the roof is too thin, the foundation is weak, and the water supply is unstable, the house will still be difficult to inhabit for long. The same is true for planets. Distance from the star determines where the house is placed. Everything else determines whether that house can truly support life. Mars is like a house that once had more favorable conditions than it does today. Its roof may once have been thicker, meaning its atmosphere may have been denser. Its interior may once have been warmer and more active. Water may once have flowed across the surface. But over time, the roof grew thinner, warmth escaped more quickly, water withdrew from the surface, and the house became colder and drier. It did not collapse completely. It still stands, preserving old evidence within its rocks and ice. But it is no longer the stable environment it may once have been. This helps us view planets beyond the solar system with greater caution. When humans discover a planet orbiting another star, one of the first things scientists consider is its distance from that star. If that distance places it within the habitable zone, it is an intriguing sign. But it is only the beginning. We still need to know whether the planet has an atmosphere, how thick that atmosphere is, whether it can survive for long periods, whether water is present, how hot or cold the surface is, and whether the parent star is active enough to erode the atmosphere. Even a planet close to Earth in size is not enough to draw a conclusion. If it lies too close to its star, it may lose its water. If the star is too active, the atmosphere may be exposed to powerful disturbances. If the planet is too small, it may struggle to retain gas. If its interior cools too quickly, its magnetic field and geological activity may weaken. If the atmosphere is too thick, the planet may instead become excessively hot. Every factor matters, but the final environment is determined by the way all of them work together. Mars therefore becomes a lesson close to home. It lies within our own solar system, near enough for humanity to send orbiters and rovers to study it. It preserves evidence of ancient water, ice that still exists today, a thin atmosphere, and rocks that record many stages of environmental change. It is not a distant world known only through faint data. It is a clear example of how a planet can once possess more favorable conditions and then gradually lose the ability to preserve them. That lesson does not make Mars less fascinating. It makes the planet even more important. If we search only for worlds that are completely Earth-like, we may overlook the many stories that exist between two extremes. Worlds that are not fully habitable, but are far from meaningless. Mars occupies that middle ground. It is not a second Earth, but neither is it an empty rock. It is a world that once had water, once had a thicker atmosphere, once experienced conditions different from those of today, and then preserved evidence of how those conditions changed. By studying Mars, humanity has learned that habitability is a story of balance. Too much heat or too much cold can both create difficulties. With too little atmosphere, water cannot remain stable. Excessive activity from a star may gradually erode the atmosphere. Gravity that is too weak makes it harder to retain gas over long periods. If the interior of a planet cools too quickly, its protective systems and geological activity may decline. Water needs to be present, but it also needs time and an environment stable enough for it to play its role. Mars once possessed several pieces of that larger picture. It had water. Its atmosphere was thicker than it is today. Its geological activity was stronger in its youth. It preserves evidence of ancient lakes and minerals that once interacted with water. But those pieces may not have remained in place long enough, or may not have been stable across the entire planet. Earth is different. Earth not only has water, but has also maintained its atmosphere, temperature, active interior, and natural cycles over extremely long periods. That difference helps explain why two nearby rocky planets within the solar system followed such different paths. From a broader perspective, every planet is a natural experiment. Venus shows how a world can become too hot. Mars shows how a world can become too cold and lose too much of its atmosphere. Earth lies between them, not only because of its distance from the Sun, but because many conditions have worked together to preserve balance over long periods. When we examine these three rocky planets together, we begin to understand that life requires more than a favorable location. It requires a history stable enough to endure. This makes the question of life in the universe even deeper. When searching for distant planets, humanity does not ask only whether a world lies at the right distance from its star. We also ask whether it can retain an atmosphere. Does it have water? Is it too hot, too cold, or too unstable? Is its parent star excessively violent? Has the planet had enough time for its environment to become stable? These questions are difficult to answer, but Mars helps teach us which questions need to be asked. When we turn back toward the red planet, we see that it is more than a place that once had water and then dried out. It is a clear reminder that a habitable world requires many conditions to exist together. Water is necessary, but it is not enough. Light is necessary, but it is not enough. Atmosphere, gravity, temperature, internal activity, and time all contribute to the story. Only when many of these factors remain in balance does a planet have the opportunity to become a place where life can emerge and continue. Mars did not preserve that balance in the way Earth did. Yet this is precisely what makes it such an important world to study. Its rocks preserve evidence of water. Its ice holds part of the water that remains. Its thin atmosphere contains the story of loss. Its cold and dusty seasons show a present that is still changing. And within that entire history, we can see a broader lesson about what a world needs, not only to possess water for a brief moment, but to preserve a habitable environment across immense spans of time. By the end of this journey, Mars no longer appears as simply a cold red planet far from Earth. It becomes a very long story about what once existed, what changed, and what still remains in many different forms. Across its surface, water once passed through certain regions, leaving behind dry river channels, ancient lakebeds, sedimentary layers, and minerals that once interacted with water. Beneath the cold ground, some of that water still sleeps as ice. High above, a thin atmosphere continues to surround the planet, far weaker than it was in the past, but not completely gone. Mars is not an empty world. It is a world that has been changing for so long and so slowly that its greatest losses can now be read only through rock, dust, and ice. If we could stand on Mars today, we would not see a sky like Earth's. The air there is extremely thin. The sunlight is weaker. The ground is cold, dry, and covered in red dust. Valleys that may once have carried water toward lower regions now remain only as lines carved into stone. Places that were once lakes no longer hold a surface of water, only layers of soil and rock resting one above another like remnants of a very distant age. That sky is still a sky, but it is no longer heavy enough to retain warmth, no longer under enough pressure to keep liquid water stable for long, and no longer thick enough to make the red planet a gentler place, as it may once have been. What gives the story of Mars its depth is that it cannot be explained by one single cause. The planet did not become dry because of one storm from the sun. It did not lose most of its atmosphere in a single day. Nor did its water simply evaporate and disappear entirely into space. Everything happened through many connected processes. Mars is smaller than Earth, so its gravity holds gases less strongly. The planet's interior cooled more quickly, causing activity deep within it to weaken earlier. When its magnetic protection was no longer as strong as before, the upper atmosphere became more vulnerable to the streams of particles coming from the sun. It is this slowness that makes Mars such a memorable reminder. A planet's fate does not always change through violent collisions or enormous disasters. Sometimes the transformation begins with losses so small they are almost invisible. Gas escaping from the upper atmosphere, shallow lakes gradually drying, ice shifting with the seasons, rocks being altered by past contact with water, and dust carried by wind across the red plains. None of these processes is large enough to transform an entire planet immediately. But across millions and billions of years, these quiet changes accumulate into a different history. A world that once experienced wetter periods gradually becomes the cold, dry Mars of today, beneath a thin sky, with traces of water preserved in stone. And from that red planet, our thoughts return to Earth. The blue sky above us is often treated as something so familiar that it hardly receives our attention. It is there every morning, above rooftops, behind the branches of trees, over the ocean, and across roads after the rain. We breathe within it, move through it, and depend on it for life, yet rarely stop to feel how extraordinary that layer of air truly is. Only when we look toward Mars do we see that a thick and lasting atmosphere is not something to take for granted. It must be held by gravity, strong enough to keep it close. It must be protected to some degree from the influence of the sun. And it must remain connected with water, rock, oceans, climate, and processes deep within the planet across immense spans of time. Earth is larger than Mars, so it holds on to atmospheric gases more effectively. Earth's interior remains active enough to sustain many important processes. Our global magnetic field quietly deflects many charged particles arriving from the sun. The atmosphere is thick enough to retain heat, create pressure, and allow liquid water to remain on the surface. The oceans are not simply beautiful landscapes. They are part of the climate system, where water evaporates, forms clouds, falls as rain, flows through rivers, returns to the sea, and continues its cycle. These processes happen so regularly that it is easy to forget how many conditions must work together to preserve their balance. On Mars, the remaining water survives in ice, rock, and traces left behind. On Earth, water still moves before our eyes. It falls from clouds, flows through rivers, rests within the oceans, sinks into the ground, and passes through living bodies. Something that feels completely ordinary to us is something Mars could not continue to preserve. This difference does not make Mars less valuable. On the contrary, because it is different from Earth, it helps us understand our own planet more deeply. Mars is like a quiet mirror placed within the solar system. In that mirror, we see a rocky world that once had water, once possessed a thicker atmosphere, and once experienced stronger internal activity, but could not preserve those conditions in the way Earth did. It is not a failed copy of the blue planet. It is a world of its own, with a history of its own, and that history helps us recognize how difficult it is for a planet to maintain a habitable environment over long periods. A world capable of supporting life requires more than a moderate position around its star. Distance helps determine whether a planet receives a suitable amount of light, but that is only the first condition. Its atmosphere must be thick enough to retain heat and create pressure for liquid water. Its gravity must be strong enough to prevent that atmosphere from escaping too easily. The interior of the planet must also remain active for a long time, so that protective systems and geological processes do not fade too early. Water is extremely important, but water cannot protect itself. It needs an environment stable enough to remain, to flow, to interact with rock, and to help create conditions that endure through time. So life, if it ever has an opportunity to appear on a planet, requires more than a brief, favorable moment. It needs a balance that can be maintained long enough. Mars teaches this lesson quietly. Dry river channels tell us that water once had paths to follow. Minerals within the rocks tell us that water once touched the surface and altered the material around it. Ice beneath the red dust tells us that water has not completely left the planet. The thin atmosphere of today tells us that a layer of air can gradually be worn away. Each of these traces forms part of a larger lesson. A planet does not only need a favorable beginning, it must also preserve its conditions for long enough. When our thoughts return to Earth, familiar things suddenly take on a different depth. A cloud drifting across the sky does more than soften the landscape. It shows that water is still circulating through the atmosphere surrounding the planet. Rain falling onto the ground is evidence that Earth continues to retain the warmth, pressure, and water required for that cycle to continue. Even our ordinary breathing becomes more remarkable, because behind that gentle act lies an entire atmosphere that has been retained, protected, and sustained for a span of time far greater than any human lifetime. Perhaps the deepest impression Mars leaves behind is not only the feeling of a world that lost liquid water from its surface. The red planet helps us understand that the air surrounding any world may be more fragile than we imagine. Water does not always remain in familiar forms. It can freeze, seep into rock, become locked within minerals, or be broken apart and gradually lost to space. A planet's fate does not change within a brief moment. It is written through small, slow, repeated movements across billions of years. From that story, Earth's blue sky emerges as something far more precious, quiet and familiar, yet holding clouds, oceans, rain, and every breath of life. Mars continues on its orbit around the Sun in its own silent rhythm. Across the red plains, dust is carried by the wind and later settles again. At the poles, ice changes with the seasons, expanding in the cold and retreating beneath the faint sunlight. Ancient river channels remain in place, no longer carrying water, yet still preserving the memory of a time when the surface was different. Within that silence, the red planet tells its story through what remains. Its water did not disappear through one single pathway. Some left the planet, some froze, some entered the rocks, some remained within minerals. What once moved across the surface changed into quieter forms. Mars is therefore not only a place of loss, but also a world that preserves the memory of earlier ages for an extraordinarily long time. Earth, following a different orbit, remains surrounded by a sky that is thicker, wetter, and bluer. Beneath that sky, water still flows, clouds continue to form, winds carry moisture across continents, oceans hold most of the planet's water, and life continues in countless forms. When we place the two worlds beside each other, we see more than a difference in color. We see a difference in history. One planet lost most of its ability to preserve liquid water on the surface. The other has maintained those conditions until today. So when we look at Mars, we are not only looking at a distant red desert. We are seeing a gentle reminder of the value of the blue sky surrounding Earth. This layer of air is not merely a background for sunny days or cloudy afternoons. It is the invisible roof above the oceans, rain, rivers, forests, and every breath. It accomplishes extraordinary things in silence, retaining just enough heat, creating just enough pressure, and offering just enough protection for water and life to continue. As this journey comes to an end, the image that remains may be very simple. On one side is Mars, red and cold, with rivers that have become traces and a sky as thin as a distant memory. On the other is blue Earth, where the atmosphere still embraces oceans and clouds, where water continues to move, and where every breath still arrives gently. Mars helps us understand what a planet can lose. Earth helps us feel what is still being preserved. Between these two worlds, the blue sky no longer seems ordinary. It becomes a fragile, quiet balance and something deeply worthy of our appreciation.